Yes, sorry.
So, good morning, everybody. It is my great pleasure to present our next invited speaker, Apurva Khare. He made his bachelor degree at the Indian Statistical Institute in Calcutta, and then decided to move for his PhD to Chicago, to the University of Chicago. And he finished his doctorate in 2006. And after that, he held several postdoc positions at the University of California at Riverside, at Yale, at Stanford. And then 5 years ago, he went back to his home country, to exactly this place here, to the Indian Institute of Science, where he is professor now. So his background is in algebra. His thesis is on representation theory of algebras, but he's still doing that, but he has branched out in several directions since then. So you'll find papers in group theory, geometry, more precisely theory of polytopes. One can even discover a paper in number theory. And he has developed a strong interest in linear algebra and analysis, where he's interested in positivity and total positivity of matrices and operators. And he has become interested in combinatorics, where I believe the link is formed by the Schur functions. So for his scientific work up to today, he was just this year elected fellow of the Indian Academy of Sciences. And we are now looking forward to his talk, which indeed is on Schur functions, namely inequalities and equalities satisfied by them.
Okay, yeah. So first of all, thank you very much to Christian for the extremely kind introduction and very comprehensive one. So yeah, I was actually going to start by saying that my PhD is in representation theory, and then recently I have been, and so representation theory, the name of Schur, of course, is very well known. Schur polynomials are characters of representations of semi-simple Lie algebras and of the general linear group. Recently, I've branched out as well into analysis and matrix positivity. And the name of Schur shows up there as well in terms of something called the Schur product theorem, which tells you things that help. So it's about functions that act entry-wise on matrices. So if you've seen some analysis and sort of the spectral calculus, you know functions act on the eigenvalues of symmetric matrices. But there's also research on functions acting entry-wise on matrices in analysis. And the Schur product theorem is one of the first results about in that direction. So Schur himself was, of course, a remarkably versatile mathematician. There is an entire survey by Dim and Katz-Nelson. You can find it on the archive on the contributions of Schur in analysis, and it is about 100 pages long. So he had many, many things to contribute in many different fields. And so my interest in even in the in algebraic combinatorics showed up from the analysis side, starting from the Schur product theorem and going down a long line of results. The interesting thing was in that analysis side, eventually Schur polynomials from representation theory turn out to play a rather important role. And so I will try to tell you some of those connections today, how exactly Schur polynomials show up in analysis. Right? So hence the term inequalities. So yeah, so let us begin then with Schur polynomials. And so these I will denote with a so I will use slightly different convention than what is known in the literature. So given a decreasing n tuple of integers, these are the powers, the exponents. The Schur polynomial over a field, let's say characteristic 0, Z, or so Q or R, is, so you take this generalized Vandermonde matrix. So two changes. One is that I'm adding the staircase partition to the powers. So that's why I have strict inequalities here. And one is that I'm taking finitely many variables, not infinitely many. Okay? So I just take therefore n many variables, n many powers, and I take the square matrix. I take the determinant. If you switch to variables, if you switch to rows, it's alternating. So it's divisible by ui minus uj, and hence by their product, which is exactly the Vandermonde determinant here. Right? So therefore, the ratio is an actual polynomial function, and then you can extend it to the entire field from distinct entries. Yeah. So anyway, this is the Schur polynomial. This is the Vandermonde determinant notation. Okay. So as Christian mentioned as well, so Schur functions show up in somehow both these areas. So they are the characters of irreducible representations of GLN or the Lie algebra of SLN, and they are a basis of homogeneous symmetric polynomials. Yeah. So the only the distinction, the notation to keep in mind is that I will use strict inequalities because I'm adding the staircase partition. Okay, and then one has this while dimension formula. I guess if you set all the variables to 1, you get a ratio of the differences of powers by j minus I. Those are one Vandermonde by another. Okay, so this is one way to define Schur polynomials, I believe, from Cauchy, and then this is attributed to Littlewood using semi-standard Young tableau. So here, so just as an example, which of course to set notation, but I will come back to it later. So 2 examples. One is again, so I'll keep n equals 3, and let's take the powers to be 4, 2, and 0. So as I said, since I already added the staircase partition, I must subtract it to get the shapes. So I have 420 minus 210, the staircase partition, sorry, I should have mentioned the staircase partition is 210 for 3 for n equals 3. Right? So you subtract from this 210, you get 210. So you draw diagrams like this with 2 cells in the top row, 1 cell in the next row, and 0 cells in the bottom row. And you have n equals 3. So you fill these cells with the alphabet 1, 2, and 3 with the rule. So without the letters, this is a Young diagram, and then once you fill them in, you get a Young tableau. And what are semi-standard Young tableau? The rule is that entries must weakly increase along each row, and entries must strictly increase along each column. So there are these 8 different fillings that you can get, semi-standard Young tableau. And now what you do is for this, you write down u1 squared u2 plus u1 square u3 plus u1 u2 square, and you write all these 8 letters down, 8 monomials down. So the weights of each tableau. These 2 give you the same monomial, so you get a coefficient of 2. And this is the Schur polynomial. So this is the other way of defining it. And in this particular case, it's very easy to see that this polynomial is exactly the same as the previous definition, because 4 to 0 means you're taking the generalized Vandermonde with these powers, but that's just the usual Vandermonde with the squares of the variables. So you get the product of ui square minus uj square divided by the usual Vandermonde, ui minus uj. So you get ui plus uj. Right? So these two definitions give you one and the same thing. That's a theorem, of course. There are several proofs in the literature, but yeah. So from this definition, you see that Schur polynomials are homogeneous and symmetric because you're dividing an alternating polynomial by the Vandermonde. You don't see that the coefficients are positive integers, non-negative integers. From this definition, you see that the coefficients are non-negative and they're homogeneous, but not that they are symmetric. Okay, another example. So let's say the powers are 3, 2, and 0. Then I, again, first subtract the staircase. So I get 2, 1, and 0. Sorry, I subtract that. I get 1, 1, and 0. And I know that one cell here, entries must strictly increase. So these are the only 3. Okay, so I will, as I said, come back to these 2 examples later for the inequalities side. Okay, so now let's begin with the equalities side. So I want to tell you about a couple of, hello? Yeah. So a couple of very classical results, which we all know. Well, actually the first one everybody knows, I think. Yeah. So yeah, so this is Cauchy's result. And interestingly, this might be the first place that I have seen a function acting entry-wise on matrices, and it is not in analysis. Although that's what I like to do, work with. But yeah, so take a function, and I'll define f square bracket a to be the function acting on aij. So the matrix you get by each entry being transformed. Now take 2 vectors ui and vj, and so apply the geometric series entry-wise to each function. What you get is, and then take the determinant, you get this beautiful formula, which is, well, you just get vu times the Vandermonde in the u's, because this is alternating, the Vandermonde in the v's, and then the sum of the Schur polynomial in u times that in v for every tuple of powers. And I'm just splitting it according to the sum of the powers and then these partition it. Except again, the slight notational issue of this being not, partitions, but strictly decreasing tuples of integers. But yeah, they denote, that's just the notation thing. The idea is the same. The identity is unchanged. Okay, this was generalized a few decades later by Frobenius, extended to a sum of 2 geometric series. And then this is the, so 1 over 1 minus t is one geometric series, and then ct over 1 minus t is another. And then you get a similar expansion. Again, you get the Vandermondes to come out. And there is some factor as well, a scalar factor. And then you get this sum. So, okay. So maybe I don't know if one can move this slightly. Sorry. Yeah. There's just a question there. And the question is, what happens for other power series? Yeah. So, thanks. So let's look at some easy cases, I guess. So suppose so I write down f as a polynomial with, let's say, less than n terms. Oops, sorry. Yeah, with strictly less than n terms. The point is, if you apply any single monomial to a matrix ui times vj, then you get ui to the n1, vj to the n1. So if you apply it to a rank 1 matrix, you still get a rank 1 matrix. And so when you add up k many of them, and if k is less than n, then this matrix is singular, so its determinant is 0. Easy. Sorry. What if there are exactly n terms, as many monomials as the size of the matrix? Then now you potentially get a full rank matrix. So in that case, it's different, but this is exactly the classical case, if you will, because then you'll write down this matrix. It actually factorizes as a product of 3 square matrices. The outer matrices are generalized Vandermondes, so you know the determinant. That's exactly the Schur polynomial times the usual Vandermonde. The inner matrix is diagonal, so you know the determinant. So yeah, so this is easy again. And now this recipe tells you how to work it out for every polynomial. You write down a long matrix at the beginning, and then a tall matrix at the end, and a huge diagonal matrix, and use something called the Cauchy-Binet formula. Okay, so to take so many, every n, every subset of n many columns here, the same subset of n many rows there, and then you multiply with the corresponding monomials, f product of the fj's. Okay, so that was about the algebra side. We next come to, as I said, the fact that entry-wise functions were studied in analysis. And so they were studied as early as, sort of morally speaking, by Schur, but explicitly identified by Polya and Zigo in 1925, in the 1920s. And then over the years with Schoenberg and Rudin and other people. In the 1960s, so we are moving ahead in time now, Loevner, Charles Loevner, studied the same idea, but now with over the real numbers, not algebraically, as a function of t. So let's say you have a smooth function, you take, if you fix a vector u in Rn, and let's say take pairwise distinct entries, so you don't just get zeros when you take determinants, right? You don't get two identical rows or identical columns. And now define this delta of t. This is his notation for the determinant of f of t times u transpose. Right? And because f is smooth, this function is smooth, you can start computing its Taylor coefficients. What do you get? So what Loevner saw was the first n choose two derivatives. So the 0th order, the first order, and so on. The first n choose two derivatives are 0. Basically, because when you evaluate it at non-zero, and this is what you get. So it's the Vandermonde square, and then you get product of these Taylor coefficients, if you will. What Loevner, it's a joke, of course, but what Loevner missed is that he missed a factor of 1 square in this expansion, and well, so that was what sort of yeah, that has implications. So. So the reason why Loevner was looking at this was something to do with functions acting entry-wise on matrices, on positive semi-definite matrices, matrices whose eigenvalues are bigger equals 0. And then some question about when you start with a rank 1 matrix like this and you start with a function and it preserves positivity. So what you get later on also is positive semi-definite. For which smooth functions does that kind of thing hold? And so he was looking at it for some analysis reasons, which, as I said, I also look at now. But what if he had, so he didn't need anything more than this formula, and he stopped there. But what if he had gone one step further? Then he would have seen that he missed something more, right? So then you get a Schur polynomial, the simplest one. This is the Schur polynomial for one cell, one row with one cell in it. This is the Schur polynomial for 0 rows. Or for 0 cells, this is the Schur polynomial for 1 cell. Okay. And you get the same kind of products of derivatives. So the point is, yeah, you have to take distinct number of derivatives of different columns. So the only way you can do this for n choose 2 is if you take 0 derivatives, 1 derivative, n minus 1 derivatives. The only way you can do it for n choose 2 plus 1 also is you take 0 derivatives till n minus 2. And then the n minus first derivative, you have to differentiate further in that column. Okay, so this is what he got. And so Loevner was at Stanford, of course. So as Christian mentioned, I used to work there before coming here. So I went one fine day to the library. So I should point out, Loevner Loevner found this calculation, and at least communicated it in October 1967. And he passed away about 2 or 3 months later. So this was one of the last things he did. And when he passed away, all his papers went to the library, Stanford Library. So I went there and I asked for those and leafed through those papers, browsed through them. And I found this handwritten letter to Josephine Mitchell, where he said, I got interested in this following question, that f be a function defined on some interval, some domain. Consider all real symmetric matrices, which are positive semi-definite of a fixed order n with elements in that domain of f. What properties must f have in order that the matrices entry-wise f of aij are positive semi-definite? And I found that if f is n minus 1 times differentiable, then the function is non-negative, the derivative is non-negative, and so on and so forth. All the first n order derivatives are non-negative, and then some counterexample for trying one more derivative to be non-negative. and so on. The proof is obtained by considering matrices of the form I essentially told you. And then you see here's the determinant I found. No, the first non-zero term, I guess, in the Taylor expansion of delta. Delta is the determinant here. Is exactly the product of these Fs and then this van der Waals square. Right. So you see the one is missing. Right. So yeah. So anyway, then the letter goes on, but so this is the calculation he had done. And later on, so he told his PhD student about it, Roger Horn, who is the author of Horn and Johnson, Matrix Analysis. So Roger's paper, this might have been his first paper. It presented this result, citing Loevner. Okay, so this seems to not have been discovered before. And so in general, you can work with, instead of U times U transpose, which is what Loevner did, you can work with U times V transpose. Hardly anything different. But so yeah, let's say we are given a function formally. So to formally state the question, given a function on some domain, let's say a smooth function, take pairwise distinct scalars. We don't need that. We can put the van der Waals in the numerator and set the delta of t to be this thing and compute its derivatives. Right? So that's what Loevner was doing. And so you can even set U times V transpose, and that turns out to uncover every single Schur polynomial in the correct degree for the correct derivative, order of differentiation. Right? So fix U and V, then so let's say positive scalars, take delta of t to be this function. Then the Taylor coefficient is exactly along the same lines. Yeah, so this is in the real topology, but you can also present an algebraic version of this fact, and you can find the same details in the same place. So in some sense, every Schur polynomial occurs inside every smooth function. Okay? I should have said, if you have questions, yes, please.
The sum is over all partitions of M, so you don't add the staircase there.
Again, these are
the sum of the ends is really M.
Yes, in this case, the sum include with the staircase is M.
The notation for partitions is the usual one.
Sorry?
The notation for partitions for
yeah, everything is here. Everything includes the staircase. Yeah, yeah. The reason I'm including the staircase may not be obvious here. It will show up when I do majorization inequalities. Then I really need the partitions to have staircases. Well, the NIs are strictly distinct. For example, the simplest case was here. The NIs have to be distinct here. Yeah, and here as well. So yeah. Sorry. Yes. So yeah, all the notation throughout the talk is the NIs are distinct and strictly decreasing. And that will be needed when I do majorization. So that's why I could have done, I didn't want to do half and half, not use the staircase and then use the staircase. Okay. So this, yeah, so this is, so now if f is a power series, then so is delta. You can, so instead of taking a smooth function, take a nicer smooth function, like a polynomial or a power series. In that case, what is the expansion of this delta? It's basically when you add this up, that's what you get, right? And but this is exactly the problem that Cauchy and Frobenius had considered sort of algebraically, and now Loevner essentially was leading up to it through his matrix analysis. So yeah, so this is maybe not too hard to show, but the point is this is true in both commutative unital ring in the algebraic setting, convergence in the formal or t-adic topology, and true in the real analysis setting, the real topology with some suitable inside some suitably small radius. So yeah, when you write this formula down, you get, you can first of all also grade it by the total degree and then write this thing down. Okay, this is one example of, sort of symmetric function identities that follow from starting from Cauchy and Frobenius. There are plenty of others. These are just a small sample of other people who have worked on it over the years. And so, including, of course, in the sessions chairs works, you can find a bunch of them as well in this sessions chair. Yeah, so one small thing I want to, so let me end this part of the talk then with a small extension in one direction, which is you can go from determinants to, for example, you can ask what happens if I take the permanent. And then so this is joint with Siddharth Sahi of Rutgers. So we answer this, so we wrote down this formula for permanents. And the interesting thing was, so this was proved, this can be proved in several different ways. One is somewhat formally, algebraically, and so on. One is using the Cauchy-Binet formula. What we proved with Siddharth Sahi was we worked out a shorter proof than this using group representation theory of the symmetric group. And that same proof basically shows this formula as well, and works for every single irreducible representation, not just the one-dimensional ones. So you can work it out for all immanents, not just for the symmetric group, but for subgroups of Sn, similar formulas exist. But then one can also do this for, so this is the formula, or the previous one, when the variables commute, the UIs commute, UI uj equals uj ui, and vi vj equals vj vi. But you can also do this for anti-commuting UIs and anti-commuting VJs. How they interact is a different matter. That can be anything. But so if you have fermionic UIs and fermionic VJs, then one gets some similar identities. Those are finite, of course, because even the square is 0. Okay, so one potential question for thought, and again, I'm not an expert in this thing, is potentially can one extend in either fermionic or immanent or both directions of various other, symmetric function identities in these and other papers. So that's one direction to go. But this is definitely one evergreen line of study, symmetric function identities involving determinants and immanents and so on. Okay, so that was one. So that was one part of the talk, and then the other part was about inequalities, again involving functions acting entry-wise on matrices. So that's the underlying theme that Lovner, as I said, started out on, and Polya and Zigo and Schoenberg and Rudin before him, but actually Cauchy before all of them in the algebraic side. Yeah, so the Schur polynomials lurking inside all the smooth functions actually really play a crucial role. They were sort of missing from the analysis literature. Somehow people had not thought to tap into representation theory or these symmetric functions to try and attack some of these problems. About entry-wise maps, entry-wise functions, polynomials, in fact, that preserve positive semi-definiteness on matrices. Okay? So these are algebraic functions, but they need to be studied actually as functions in analysis, namely functions with some domain of positive real numbers. Okay? And okay, so let's go back to an example. These are functions now which we have, so as I said, that's why I need them only on finitely many variables, not infinitely many. This is now an analysis question I'm looking at. So look at the function of 3 variables, and all the 3 are positive real numbers. Okay, so clearly, these are what we call monomial positive. They're sums of monomials. So there are no negative signs. Yeah. So in particular, if you look on the positive orthant, then the functions increase in every single coordinate. Yes. That's because they're monomially positive. Now you'll notice that the degree of this, the total degree of this function is bigger than that, but the lower one does not divide the upper function. Right? So if I look at the ratio of these functions, I don't get a polynomial. It is a ratio of 2 polynomials which are both coordinate-wise increasing, and which are monomial positive, in fact. But the point is, the ratio actually has the same property. It is also coordinate-wise increasing. So both numerator and denominator are monomial positive. In fact, Schur positive, meaning they are sums of Schur polynomials, because they are each one Schur polynomial, but they are also non-decreasing. It's the ratio is non-decreasing as well. So this actually again seems to not have been known in the literature. So this is a result from December 21, published December 21. So for take any integer tuples n1 through nn, then so this is where I will need on the next slide probably. So yeah, such that the mj's coordinate-wise dominate the nj's, and look at this function. This is a function defined everywhere on the positive orthant, and it is non-decreasing. And there is a stronger Schur positivity phenomenon, which I will tell you now. So this was the theorem. Let me go back to the special case of the example. And how does one prove that something is is monotone in some direction? Well, first of all, this is symmetric, right? This is a ratio of 2 symmetric functions. So it's enough to check that it's coordinate-wise non-decreasing in, I think I'll do U3 in this slide. I think I have done U3 in this slide. Yeah, so how do you check that something is monotone? You take the derivative and hope it's positive, right? So take the derivative, the usual way we teach it, low D high minus high D low. And notice that this is actually monomial positive as well. So technically, there's a denominator square, but I don't care because I'm looking at the sign of the derivative. So this is monomial positive, and so on the positive orthant, it's numerically positive. Right? But there's something stronger that's going on. So this is clearly not symmetric in the 3 variables, but it is symmetric in 2 variables, right? It's differentiated with U3. So in U1 and U2, it stays symmetric. Let's look at the coefficients of each monomial, each power of U3. So it turns out that every such function is actually a sum of Schur polynomials. So there is some Schur positivity embedded inside this derivative being numerically positive. So there's a U3 here, so there's no constant term. U3 power 0 has no term. U3 power 1 has the coefficient, this coefficient, which is exactly a Schur polynomial, plus a Schur polynomial itself. And then the coefficient of U3 square is U1 plus U2 square, I guess. So the coefficient, that's U1 squared plus U1 U2 plus another U1 U2 plus U2 square. And that's a sum of 2 Schur polynomials. So that was something pretty surprising to us. And then but the proof is exactly the same for general number of variables and general powers, I guess. Yeah, so by symmetry, you do the same thing. You hope it's numerically positive. It would follow if this is monomially positive. And in fact, you do the same check and it's Schur positive. The key result we use here is a really strong identity by Lamb, Postnikov, and Pilyavsky in 2007. But that in turn emerged out of work of Marx Kandera on totally non-negative matrices, which also is some fascinating paper. Sorry. So, okay, so that was a nice fact, but now that's what consequences does that fact have is where I'm going with this to majorization. So this lemma implied that if you take, M dominates N coordinate-wise and you look at the ratio on the positive orthant, but actually on a smaller part of it. So these are the coordinates where each entry is bigger than 1, meaning the log is positive. So let me call it the log positive orthant. So if this beats so we know that if U is in the log positive orthant, then this ratio beats the ratio value at 1s. And as we know from the Weil dimension formula, that's just the ratio of the van der Waals of the powers. So it's natural to ask this question, is it only these powers, is this dominating phenomenon that works, or does it work elsewhere? It works elsewhere. And it works not just for integer powers, but it works for real powers. But how do you define this thing for real powers? So the way you define it is you multiply and divide by the van der Waals in the variable U. Then you just get a generalized van der Waals matrix by the Cauchy definition. And that's what we look at. So this is the matrix UI power mj and UI power nj. Okay, so the ratio of the van der Waals, generalized van der Waals, beats that term for all tuples, except I have a denominator here, so I cannot take, so I have to take unequal coordinates. It's a dense set, so in analysis, that's fine, right? Sorry. So yeah, this ratio beats the above ratio, the value at 1, 1, 1, 1, 1, or the limit at 1, 1, 1, 1, 1 for all distinct tuples, if and only if M weakly majorizes N. So again, starting from Schur polynomials, in algebra, one gets to basic inequalities of real numbers, so weak majorization, meaning and the ingredients are, so we had to come up with something called a first order approximation of Schur polynomials, or basically isolate the leading term of Schur polynomials. And when you have leading terms, again, this is analysis. And then one uses this Harish-Chandra-Zuber integral and a Schur convexity result. But that's the one that connects to majorization or weak majorization. It turns out, of course, that, or not it turns out, this kind of idea to connect Schur polynomials to weak majorization was not new. It was done about 10 years ago for majorization. So what Cutler, Green, and Skandera did in the 2010s was they looked at the same inequality, this inequality, but now instead of just the log positive orthant, look at all of the positive orthant. then what happens? So the point is, suppose m has total degree bigger than n, right? Then, then on the log positive orthant, sure, it can dominate as asymptotically. But when m has total degree bigger than n and the u goes to 0, then this inequality should get reversed. So at least you know that the total degree should be the same. And once you have the total degree is the same and this holds, that's called majorization. Right? When you have the total content of the m's and the n's to be equal and this holds, then you get majorization. And so that's exactly the result that they proved, that if this inequality holds on the full positive orthant, then then m actually majorizes n. And they asked the question, is the converse true? If m majorizes n, is this inequality true on the entire positive orthant? That turns out to be true. That was proved by Fpsac 5 years later after their conjecture. So this is the result. Fixed integers, pairs of powers, and I will keep adopting the same notation with strict inequalities. The Schur polynomial beats the value at 1, 1, 1, 1, 1 throughout the orthant now, not just log positive, but if and only if m majorizes n. And that's so part of it is essentially why I told you. Okay, so then, so one can of course ask now, first of all, does this hold for real powers? I mean, what's special about integer powers? And secondly, do you need the entire positive orthant, or can you work with a smaller set? Yeah. So to deduce, to deduce that m majorizes n. So yes and yes. So given any pair of real tuples, and I don't need it to be positive or non-negative or anything, the following are equivalent. First of all, this inequality holds for all. Again, I need to take distinct tuples yeah, and take generalized Vandermonts instead of Schur polynomials. If and only if it holds for all distinct tuples in the log positive orthant and the log negative orthant. So I don't need the rest of the information. Actually, even this can be weakened to one sequence, countable sequence here and countable sequence there. But anyway, if and only if m majorizes n. So first of all, the takeaway from this at least is that majorization, just like weak majorization, can be worked out for real tuples in terms of Vandermonde matrices, not just, I mean, it's slightly more general than for integer tuples in terms of Schur polynomials. The reason is because I'm going to tell you about a vast generalization of this by Maxwiggen and Novak. So, okay, since I do have some time, I'll give you a small sketch of one of the parts. So if it works for all tuples, it works for, a smaller set. That's obvious. 3 implies 1. If it majorizes n, then this holds. So Fpsac proved it when these are non-negative integers. So the proof in general goes through pretty much the same way. Sorry, with Harishchandra at 6 and Zuber's integral. The part I want to tell you quickly is why 2 implies 3 follows sort of relatively straightforward from our previous result. So this is sort of a strengthening of Cutler, Green, and Skandera in 2 ways. One is the powers are no longer integers, and this is no longer, the full orthant is not needed. So no, I thought I will put at least one proof in the talk. So this is that proof. Yeah. So if u belongs to the log positive orthant and we have this inequality, then we know that m majorizes, weakly majorizes n. That was by our previous result with tau. And then if u is in the log negative orthant, just invert, take the reciprocals, and then compute this ratio, first of all, the vi's to the minus mj's. But that's exactly the same as ui to the mj's. So this ratio equals this ratio, which we are given to be bigger than the ratio of the Vandermonts, which is the ratio of the negatives Vandermonts. And now if you look at the first term beating the last term, where the first term is indeed in the log positive orthant, then you get minus m weakly majorizes minus n, and we know m weakly majorizes n, and together they are if and only if m majorizes n. That's basically from the definitions. The content is the same. Okay, so that was the one proof I had in the talk. So yeah, so this was about using Schur polynomials. What if you use other things? So this is Cutler, Green, and Skandera. Let's go back to integer tuples, basically. Instead, if one uses something called the monomial symmetric polynomial, then this goes back 100 years, more than 100 years. And this is called Muirhead's inequality. Interestingly, he also had real scalar powers, as far as I know. You take a tuple of real powers, another tuple of real powers, and look at the same kind of normalized. So what I did in the previous formulation was the numerator and this denominator were flipped. I'm just flipping them here to write down a normalized Schur polynomial beats a normalized Schur polynomial. The same kind of philosophy was adopted by Muirhead earlier. The normalized monomial symmetric beats this one for all u in the positive orthant, entire positive orthant, if and only if M majorizes M. So the same conclusions using a different symmetric function. So it's very natural to ask. I don't know the answer, but if someone wants to think about it, please do. What happens if you restrict to the log positive orthant here? Or, for example, is there some subset that leads to a characterization of weak majorization rather than full majorization? Okay, that's the other question. That's the second question. And I will end with a third question. So this slide is essentially thanks to Cutler, Green, and Scandera. In their paper, they mention all these lovely they do the nice historical survey. And so there are various other inequalities of the same kind of flavor, just like there were symmetric function identities, a bunch of them of similar flavors in the first part of the talk. But these go back even earlier, by 100 years, to Maclaurin and Newton and so on. And yeah, recently, there was a vast generalization of these inequalities, majorization inequalities by Maxwiggen and Novak in a beautiful, really beautiful paper in 2022. It appeared this year. To first of all, they first of all developed the idea of W majorization, for W being a Weil group of a semi-simple D algebra. So again, representation theory comes in. The idea is very simple. There is a different characterization of majorization, right? A real tuple is majorized by another. If you take that, the majorizing tuple, I guess, look at the convex hull of all the n factorial points where its coordinates are permuted, or modulo the stabilizer. Take the convex hull, and this other point must lie inside that convex hull. That's the other definition of majorization. Well, all you do now is, for W majorization, is the symmetric group is the Weil group of type A, in type A. You look at an arbitrary Weil group, and you look at a vector in the reflection representation of that Weil group, and take, so lambda majorizes mu if mu is in the W, so convex hull of the W orbit of lambda, where W is the Weil group. Right? And then with that, they looked at, analogs of this, the Cutler, Green, Scandera, Shra identity, the theorem, and they developed a characterization of W majorization. In that case, again, but they did it in the spirit of my result with tau, in the sense that they did not, I think, needed to lie in. They did not need the indexing powers or tuple like n and m to be integers. Real numbers work. So real numbers meaning any points. Like you can talk about. Okay, maybe I should say it the other way, right? So when I gave you the n factorial convex polytope definition, that did not require the points to have integer coordinates. That could be with any real coordinates, right? And the same way, our result did not have integer powers. It could have any real powers and generalized van der Waals matrices. So the same thing for them. They did not require integer coordinates of any kind or in some lattice. So the way to generalize the analogs of these ratios of Schur polynomials or Schur polynomials are spherical functions, which, even people like Harish Chandra studied in the 1950s and so on, long time since then, on Riemannian symmetric spaces of compact, non-compact type, which led to the other two compact and flat types and so on. But it's a beautiful paper. They then conjecture that this holds even more generally than spherical functions and symmetric spaces for something that is called, I don't know much about this, Heckman of them hypergeometric functions. This would first of all extend Cutler, Green, Scandera from Schur to Jack. It would also subsume the, what was the 1903 inequality I told you? Muirhead's inequality. That is not subsumed by this so far, but that would be subsumed by, if one can prove this conjecture. And then the pipe dream, of course, is to extend all the way from Jack to Macdonald polynomials. But we invited Maxwiggen Colin to give a talk here remotely. And as far as I remember, he mentioned that even the formulation of such a more general conjecture is not known for Macdonald. It is known for the Jack, at least the conjecture. Proving it is a different matter, but the McDonald extension is not even formulated. So another thing to look at, but yeah, this is really beautiful stuff. And the fact that it extends in such vast generality and holds in such vast generality. Okay, so in the final 5 or 10 minutes, something like that, I will end with my third and final problem, which combines optimization and Schur polynomials. So again, the flavor was that Schur polynomials are very, very crucial to some problems in analysis, and they end up revealing things like majorization and weak majorization from Schur polynomials. So here is a specific class of Schur polynomials for which the Young diagram is just a single row. Right? They're called the complete homogeneous symmetric polynomials. And so, yeah, you basically take, this is the definition. And notice now here, again, inequalities. So here are inequalities. H0 by convention is 1. H2, let me look at the even degree polynomials. This is the sum of ui squared plus this. And that is the summation of the ui whole square plus the summation of ui squared, the individual power sum. And then you average it out. So clearly this is a sum of squares. This is a sum of squares. So this is a square. So the whole thing is numerically non-negative again, right? Numerically positive. In fact, it turns out that H4, H6, every even degree complete homogeneous symmetric polynomial is, again, numerically non-negative. It's in fact strictly positive, not just non-negative, it is strictly positive except at the origin. So slightly stronger. This was a result proved by Hunter, I think about 50 years ago or maybe even more. But the proof there is a one-line proof using probability by, I believe, well, at least I saw it first in Alexander Barvinok's preprint on the archive. And it says, take standard exponential variables, IID. Right? And look at this, take these scalars, U1, U2, UN in the real line, in the reals, and take this linear combination, U1, Z1 plus so on plus UN, Zn. Okay. Look at the moments of this random variable. So expectation of the kth power. It turns out that is exactly up to a scalar, the complete homogeneous symmetric polynomial. So now the point is, unless all the ui's are 0, this random variable is not identically constant or identically 0, in fact. So if the power is even and it's not identically 0, then the moment is strictly positive. That's it. Right? So which other Schur polynomials share this property? Right? Maybe there are others, not just the slides from now. So that turns out to be not so hard. Sorry. So there are no others. So none. Right? So suppose this is true, then the Schur polynomial is non-vanishing here. And if it's non-vanishing and it's monomial positive, well, okay. If it's non-vanishing, then already you can prove that the Schur polynomial is complete homogeneous symmetric, and therefore strictly positive. That was by Barvinok's observation. Right? So if it's always non-vanishing, then it is always positive, except at the origin. Okay? That was not too hard to prove. That's just an easy calculation. But now let me tell you why I care about this property. It's because of the following. So the question that I have. So let me remind you of this Schur monotonicity lemma. That if you have integer tuples and you take this ratio, then and I stick to bigger equals n, m bigger equals n in each coordinate. So then this is non-decreasing. And in particular, I want to know where is the supremum on the unit cube, on the punctured unit cube, because this is not defined at, this is, at the origin. So let's avoid the origin. So it takes its supremum in the punctured unit cube at the top point. It's coordinate-wise non-decreasing. I want to understand this question over -1, 1 to the n, not just 0, 1 to the n. Okay? But if I want to do this over -1, 1 to the n, then I need to find a polynomial. I need to find integer tuple for which I am guaranteed that this doesn't degenerate at random points. And at least one safe choice is to say, well, let me choose an integer tuple for which the denominator never vanishes. Then I don't care. And I mean, I can say non-vanishing on the full thing or on a compact ball around the origin just by homogeneity, right? So I just want it to not vanish on the unit two-sided cube or on Rn minus 0. So that's why That's why it's at least a safe choice to start with a complete homogeneous symmetric polynomial and now ask the same question. Does one know what the behavior of this is? I don't even sort of, so, okay, fine. Let me ask the question first. So suppose n is this tuple of powers and m, again, the numerator powers beat the denominator powers coordinate-wise. Define the same ratio. Right? Now I know that, I mean, this can become negative in other orthons, but the denominator is never negative because it's a homogeneous polynomial of even degree. Right? How does this function behave? More precisely, what I care about only, in some sense, I'll tell you why, is where does it attain the supremum? Is it, I mean, I don't even care where it attains the supremum. I want to know what the supremum is, actually. It would be nice to know where it attains the supremum, but I just care about what is the supremum. And the point is, okay, first of all, let me just, so by homogeneity, it's enough to consider this problem is well defined. It doesn't blow up because the powers above beat the powers below. So things are of positive homogeneous total degree. So, it scales, it grows bigger. So it's enough to look at the boundary, which is a compact set. This is a continuous function on the boundary. Where is the maximum? Very simple question to state. And probably also because it's a compact set, one can run simulations or do something. I haven't looked at it yet. But the point is, if one can answer at least what the value of the supremum is, nothing else, that will already give me some extra the consequences, give us some consequences for entry-wise polynomials that preserve positivity on matrices with possibly negative entries as well. So the problem in negative entries is not as well behaved and nice as for strictly positive entries. One reason being that such a result is known, such an optimization is known for positive orthant, but not for the full set. If one can at least find out the supremum of this polynomial, even in 2 variables or 3 variables, then that would give us some consequences as well. Okay, so I think that was pretty much it. So just for, so these were some of the many articles that have been written on symmetric function identities, from Cauchy and Frobenius to Lovner. This was sort of not algebraic, but on the analysis side, some of them I think this one by Michael and Rosengren I didn't mention previously, but it's another one. And on the majorization side, again, starting from even earlier and going all the way to Max Wigan and Novak, majorization and spherical functions. And let us hope that it actually goes ahead all the way to Heckman-Opdam and even to Jack and McDonald. Okay, thank you very much.
Thank you very much. Are there any questions?
You, I guess. Oh.
Wonderful talk. That was great. So I'm wondering, after all of this, how would you define sure functions? Maybe in a new way in context using positivity?
The sure functions, I think, are the same. I mean, one way to define it is the things that show up in Lovner's calculation. Maybe, I don't know. But so one thing.
Basis, so I don't know how to phrase it that way, right? What are those functions? Are some factors that come up in this expansion?
Right. That would be one way to think about it. That's in some sense in my matrix positivity side. That's how I think about sure functions. They are the functions that show up when you take these identities, apply a function to a rank 1 matrix, and expand the determinant out. And they're exactly the functions that show up in the coefficients. Exactly. Yeah. I should just add one more thing, that morally, it's, morally, given this last paper with Tau, where we work things out for sums of real powers rather than just polynomials, sums of integer powers, the boundary between sure functions and generalized van der Waals determinants has started to blur for me now. So they seem to be equally well behaved in the things we wanted them to do, including even majorization inequalities. So,
Could you say a little more about what the functions are that show up for Mixwigan and Novak? What is the analog?
Great. Okay. Well, again, I'm not an expert, but sure, if you insist, let's go. I did not plant you in the audience, not the question. So yeah, so should we turn on the light or something? Maybe? If you have 2 minutes, I'll actually take you through 2 slides, which expand on what
Thank
they
you.
do. Yeah. So W majorization. So let V be a Euclidean space containing a crystallographic root system with this while group for notation. Right? So W is generated by the hyperplanes orthogonal to the roots. So we say W lambda and mu. I think adopting their notation. W majorizes mu if mu lies in the convex hull of this orbit, as I said. So special case being of type A, W is the symmetric group, and then lambda Sn majorizes is exactly the same as lambda majorizes mu. That's the theorem or a lemma, I guess. Right. So okay, so this is all the technical stuff. There's only one slide. So let G be a connected Lie group, and then you look at such a group with a involution whose fixed stabilizer subgroup is compact. That's what one calls a Riemannian symmetric space. They are of 3 types, and then under certain further assumptions which the authors make, you have this Iwasawa decomposition, and the weights of the Lie algebra form a root system. Okay, so one studies W majorization for exactly for lambda and mu inside this Lie algebra. The analogs of normalized Schur polynomials then are exactly these spherical functions. Again, there's some notation that I will state, but yeah, basically those are the spherical functions for which they. So you look at when you have to perturb by you have to multiply by I, but yeah, you look at when this function beats this function on G mod K, and that is if and only if lambda majorizes mu. So roughly speaking, and then I guess I will probably refer you to their paper. This part is from the last slide. Yeah. But beyond this, yeah. So I would just say look at the paper. But it's a very, very clearly written paper, and yeah. And the point is what they show somehow is that once they are able to prove this thing for G mod K of non-compact type, it follows the same kind of majorization inequality follows for the other 2 types of symmetric spaces. That's from a very cursory reading at their paper.
Okay. Well, thank you very much.
Some other question?
Travis.
So just kind of a follow-up on Sarah's, because she mentioned like this doesn't seem to form a basis, but can you actually extend definitions to get a basis for this in this generalized context?
Sorry, which context? I mean,
well, since
I mean, they are the same polynomials. I mean, there's no difference. So they do form. That's what they form. I mean,
but in real power, or yeah.
Oh, real powers.
Yeah, but the basis of which?
Yeah, but
space.
Yeah, well, I was thinking in terms of like
symmetric
extending all
functions
in a product in some continuous way.
I don't know of this. No, not yet. In fact, the functions themselves, if you look at, for example, just the generalized van der Waals determinants, I don't think they are very well studied in any case as functions. I mean, yeah. So I think like Tao has a blog post, which was written again, obviously, during this paper when we were working out the continuous case. He wrote down some set of observations about, I think maybe he called them continuous Schur functions or something, and you can look at that. Right. So that was exactly in this paper's writing that it happened, but that's about all that I know of. So I think it's known that they are defined only when the arguments are pairwise distinct, obviously, generalized van der Waals, but then they extend continuously and so on. Beyond that, yeah, how much kind of a basis they form, yeah, I don't know. But I mean, again, these are sort of functions that, degenerate or something to polynomials. And you could look at, for example, rational functions. You could look at ratios. So the space of symmetric functions would probably be much larger.
Yeah.
Right. So maybe one can ask, are they linearly independent or something? But beyond that, I don't know much more to say. And linear independence is probably something you can prove by isolating the leading term, which are distinct for distinct tuples. Yes, the leading terms are distinct, so probably their asymptotic arguments give you linear independence directly.
Right, thank you.
Yeah.
A small addition, Kevin Cadell wrote a paper where he extends the Schur functions to complex indices. Kevin Cadell.
Complex exponents, you mean? Complex powers.
Yeah.
Wonderful. Okay, I should ask you for that paper.
Is there another question?
Vishal has a question.
Yeah.
So you've mentioned majorization for sure and also monomial symmetric
Yes.
polynomials. But
Yes.
what about elementary symmetric or complete homogeneous?
There are some results in, so again, Cutler, Green and Skandera mention all these results. And I think elementary, at least, I think, or maybe even both of them show up in that paper. So you should look at that paper for the details. Yeah.
And follow up. E positivity or H positivity implies sure positivity implies monomial positive. Is there some relation to the story?
What is E positivity? Just sums of E's. Sums of E's and sums of H's. That's all. Okay. Yeah. I mean, in the example we had, it was it E's? It wasn't E's. There were 3 cells, right? And 2 and 1. So it wasn't E, but it still did imply monomial positivity in some sense. So, I mean, I don't know really. Yeah. Maybe that also happens. That does happen in itself, but yeah.
Right.
At least in the proof we saw, we didn't need it. We didn't use that.
Like so maybe something to do with the space. So you mentioned it's the log positive ortho, but then
Yes.
that lies within 0 infinity power, but maybe for
That's a fair point. Yes.
Inside.
Yeah, that's a good question. I have wondered, why bigger than 1, 1, 1, 1, 1? Why not 2, 2, 2 or half, 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 or what happens for other things? I don't think anything is known. Yeah, nothing is known. You get some necessary conditions or something, but nothing more than that. So characterization is not known.
Okay, I think we have to close the question period. So let us thank Apurva for a great talk again. And we continue in just a moment.
Hello. Okay, so it's on now.
Does the microphone work? Yeah.
Yes, it's working.
Okay, it seems we are ready for our next contributed talk, given by Projeshnath Chaudhuri, and his topic is Blow-up polynomials and I suppose delta matrices of graph.
Thank you. So today I'm going to talk about some new kind of construction arising from finite simple connected graph, which we call blow-up polynomials of graphs, and which turn out to have some nice properties and connections. And this is a joint work with the previous speaker, Apurva Kare. So let us set some notation. Recall that a graph G is a pair B, E, where B denotes the set of paired vertices, and where B denotes the set of vertices, and E denotes the set of paired vertices, and whose elements are called edges. And in this talk, all my graphs are finite, simple, unweighted, and the most importantly is connected. So because the graph is connected between any 2 nodes B and W, there is a path which may not be unique. Therefore, look at any path of the shortest length, and I call that length as dBW. And it is clearly a non-negative integer, and it is equal to 0 if and only if B equal to W. And with this number, we form a B by B matrix called the distance matrix of graph G, whose BW element is dBW. And the determinant of distance matrix of tree studied a lot in the literature, and recall that tree is a connected graph with no induced cycles. In other words, a connected graph with n nodes and n-1 edges. So our work is motivated by two sort of classical facts. First one is algebraic, and to illustrate this, here is an example. Take two trees on same number of vertices, and clearly they are non-isomorphic. Now look at their distance matrices. Let us say for the first graph, vertex 1 is adjacent to 2, 3, 4. So obviously all the diagonal entries are 0, and the entries 1i are 1 for I equal to 2, 3, 4. And similarly, the vertices 2, 3, 3, 4, and 4, 2 are at a distance 2 from each other, and this gives distance matrix dt1. And similarly for path graph also. It turns out that both these matrices have same determinant. And surprisingly, this holds for all trees. And this was a result by Graham and Pollack in 1971. They proved that the determinant of distance matrix of tree on n nodes is a function of n, and it is independent of tree structure. So this provided us our first motivation. We wanted to look at other such families of graphs for which the determinant of distance matrix is a nice function. And the second fact which motivated this work is from spectral theory. Ron Graham again studied the spectral side of distance matrix of tree with Lovash in 1978. And one question natural to us is the following. Of course, distance matrix itself detect the graph. Just look at the entries which are 1, those corresponds to the edges. And once you have the edges, you have the graph. Now the question is, does the characteristic polynomial of distance matrix detect the graph G itself? Or in other words, do the eigenvalues of distance matrix recover the graph G? The answer turns out to be no. There exist non-isomorphic graphs. For example, these two graphs on same number of vertices. So the distance matrices are of the same size, and the characteristic polynomial agrees for these two graphs. But these two graphs are clearly non-isomorphic. Here is a vertex of degree 4, but there is no vertex of degree 4 in the first graph. So in particular, we can conclude that the characteristic polynomial does not detect the graph. And this gives us two interrelated motivations or goals. First one is to find a family of graphs GI indexed by some set I. For example, a family of trees on fixed number of vertices, such that the function I goes to that DGI is a nice function. For example, for this family of trees, the function is a constant function, which is purely a number in terms of k. And so we also want to find the other such family of graphs. And more importantly, this motivation help us to this motivation should relate to the other goal. This family help us to find a invariant which truly detects the graph G. Of course, distance matrix itself detects the graph, but we want some kind of polynomial invariant. So the goal of this talk is to tell you, indeed, these motivations are achieved with the same object, and that the object I want to tell you is called blow-up polynomials, and the family here is called blow-up of graphs. And so let us begin with the family, then come to the invariant. So the key construction which will answer both of these questions and reveal many more interesting facts is the following. Take tuple of integers nb indexing by vertices, and I will call the new graph by G bracket n, which is again a finite simple connected graph. And the vertices are as follows. For nb, that integer that I have chosen, take that many copies of vertex b. Now connect all copies of a vertex b to the all copies of another vertex w, if and only if those two original vertices b and w are adjacent in the original graph. Also note that a copy of a vertex b is not adjacent to another copy of a vertex b because I am lacking self-proof in the original graph. So let me give you some examples. First one is a path graph on 3 vertices. So just forget about the vertex C and look at the edge AB. Now create one copy of vertex B and 2 copies of vertex A. Now A is adjacent to B. The other copy, which I will call C, also adjacent to B. But A and C are not adjacent. So the path graph on 3 nodes is an blow up of an edge. Here are two more examples. One is that of a star graph. This is exactly same as saying start with an edge and blow up one vertex with n different copies and keep one copy of another vertex. And this is exactly the star graph. And similarly for cycle graph on 4 vertices, start with an edge, namely 1, 2. Now create 2 copies of vertex 1, namely 1 and 3, and 2 copies of vertex 2, namely 2 and 4. Now 1 is adjacent to 2, so 3 must be joined to 2. So 1 and 3 are adjacent to 2. But 4 is a copy of vertex 2, so 1 and 3 are also joined to 4. But 1 and 3 are copies of the same vertex, so they are not adjacent. And similarly 2 and 4. So these are some examples of blow up of an edge. And as I said, idea is to look at the determinant. Now look at the determinant of all these blow up families. And for these examples, one can explicitly calculate the determinant, and it's turned out to be this expression. And this is very clean and nice expression, and it consists of 2 parts. One is exponential of r plus n, where r is the number of copies of first vertex, and s is the number of copies of second vertex. And then a polynomial in r and s. Now note that, interestingly, distance matrix consists of 0, 1, and 2 only, and size of the matrix includes r and s. And this is the function of sizes. Now the question is, what is the determinant of distance matrix of graph blow-ups for general graph? Does it have something similar? And here is our first result. There exists a real polynomial, PGN, n denote the sizes. So the argument of this polynomial are sizes of the matrix. And the following happens. That DGN is first of all minus 2 raised to summation sizes minus 1 times some remaining factor. And the remaining factor is a real polynomial. And this expression holds for all tuple of positive integers. And moreover, this real polynomial is multi-affine in sizes with this constant term minus 2 raised to number of vertices in the original graph and the linear term given by this. In fact, we have closed form expression for every monomial. And the real polynomial PG, what we define to be blow-up polynomial of G, covers all sizes of blow-ups, and this attains our first goal. Here the family is parameterized by bold n, and the function n goes to det dgn is a nice exponential function times a multi-affine real polynomial, and so this covers our first goal. Now the question is, does this polynomial recover the graph G? So before answering this question, let me talk about a weaker question. Suppose G is an automorphism. So by the term automorphism, I mean look at the labeling 7 and 8. If that gets switched, the entire graph stays isomorphic. Similarly, 3 and 4 and 4 and 5. So if G has an automorphism sending a vertex B to W, then the my blow-up polynomial is symmetric under this operation. Thus, we can conclude that the automorphism of G determines the symmetries of TG. Now the question is, if I know how my blow-up polynomial is symmetric in the variable, can I understand the automorphism of G? And this is the weaker question. And the stronger question is, of course, does this polynomial recover the graph G, from which I could get at the automorphism of G? And answer turned out to be yes for both of these questions. The symmetries of blow-up polynomial itself coincides with the automorphism of G, and more strongly, the purely quadratic or Hessian part of PG recovers the graph G. So these answers are our other goal also. We now do have a nice family of graphs called blow-up of graphs, whose determinant behave nicely as a function of tuple of integers, and determinant themselves are multi-affine in sizes, and which turn out to recover the graph G. Any questions?
is it possible that a graph can be obtained from two different graphs as a blow-up graph?
Sorry.
Is it possible that we can get one graph as a blow-up of two different graphs?
What?
So from a graph, we can blow up to some other graph, right?
Yes, yes, yes.
So is it happen that there are two different graphs which are not isomorphic and they blow up to the same graph? Is it possible?
I think no, it's not possible. It's not possible. Yes. Yes. Yeah.
Successive blow-ups is also a goal.
Yeah.
Yeah, like if you use the successive blow-ups, like if you just blow up a one graph, then you'll get another graph. Again, if you blow up this graph, then another graph you'll get, but these two graphs will not be non isomorphic.
Another question. As you can blow up the vertices one by one, so I wonder, is this PG a factor as a product of as many vertices as you have in the base graph? Does this factor?
The PG factor
Uh-huh.
to number of pieces. Same number of pieces.
I think no. Yes. Okay, I'll think about this, but I think answer is no. Yeah. So in the next few slides, I'll talk about some other properties of this polynomial. So remember the polynomial pk2. Pk2, this is a multivariate polynomial. Now let me specialize these two univariate polynomial. Take r equal to s equal to n. Then the univariate polynomial equal to is 3n square minus 8n plus 4. And so, and it clearly factorizes. So it is real rooted. So this is for K2, but I can also blow up the complete graph on K vertices. And if you can check that if you take the univariate polynomial UKK, then again you get a real rooted polynomial. Now the question is it real rooted for every graph? And the answer is yes, but far more is true. Real rootedness is one variable manifestation of more powerful and general notion called real stable polynomials. And recall that a multivariate polynomial with real coefficients and complex argument is called real stable if it is non-vanishing in the upper plane. And the blow up polynomial PG is real stable for every graph G. And here note that from now onwards, I'll treat this polynomial as a function of complex arguments. So the point is real stable polynomials are focus of tremendous recent research, primarily due to the work of Brochier Brandon, who proved the far-reaching generalizations of Legge-Purcell program and proved three long-standing conjectures of Charlie Johnson using this polynomial. And these progresses are then taken forward by Marcos Pillman Sivastava in proving the Cartesian-Singan conjecture and to prove the existence of bipartite Ramanujan graphs, infinite families of bipartite Ramanujan graphs. So the polynomial that I mentioned provide new examples of real stable polynomials, and that arise interestingly from graphs and distance matrices. Now, let me go beyond real stability. So I remind you from very first result, I mentioned that the blow-up polynomial has this as a constant term and the linear term is given by these things. And this shows you, this already shows you immediately that this polynomial does not satisfy two desirable properties. Clearly, there is a the coefficient of constant term and linear term are of unequal signs. So this is the first property. And to bypass this, one can consider PG of minus Z, then this minus sign goes inside and the signs are equal. But one must of course check the higher order term, the quadratic term or the cubic term. Are they also same? Similarly, there is a constant term and the linear term. So the polynomial is not homogeneous. And for this, there is a standard trick of homogenizing the polynomial. And if I want to bypass both of this operation, I have to take minus sign inside. Now the question is, why do I want to bypass these one or two obstacles? The stable polynomials with these additional properties were studied in even border settings by Brochier, Brandon, Leggett, and they call it strongly Lilly polynomials. That is, all coefficients are of the same size, same sign. And the homogeneous stable polynomials are broadly studied as Lorentzian polynomials by Brandon and Hu. And they are also studied by Vincent Anari and Anari. They called it completely log concave polynomials, and Gurbitz called it as a strongly log concave polynomials. Now the question is, if we homogenize PG at -1, for which graphs does this yield a polynomial in this class or this class? And our next result exactly characterize this polynomial. And answer is, interestingly, if and only if all the coefficients are of same size. So answer to both of these questions are same class of polynomials, and they arise from a very familiar class of graphs, that is completely multipartite graph. So given a graph G, define its homogeneous polynomial exactly the way I told you, and the following happens. The polynomial that I mentioned is real stable if and only if all the coefficients are of the same sign, and if and only if consider this polynomial without z0 but with minus sign, and divide it by pg of -1, -1, -1. That is the sum of all the coefficients. So, so you get a polynomial whose coefficients are non-negative and add up to 1, and this forms a probability distribution. And the claim is, these things happens if and only if the distribution is strongly Lilly. And all these are equivalent if and only all these are equivalent to the graph G is complete multipartite graph, which is same as saying that blow up of a complete graph. So we provide a novel characterization of complete graph in terms of real stability. In the last part of talk, I'll discuss some combinatorial extraction of this.
So related to this real rootedness, do you get some type of interlacing roots if you consider different graphs? Let's say you take some deletion or contraction in G. Do you get some type of interlacing phenomena for the roots of the corresponding lower polynomials?
I don't have an exact answer right now.
Okay, that might be something
Yes,
to
yes,
look into.
yes. I'll think about it. Yeah. So, yeah. So in the last part, I'll discuss some combinatorial extraction of these results called delta method. And recall that a metroid consists of a finite set E called the ground set, and a family of subsets of E called the independent set, which is closed under the taking subsets and independent set axiom property. Okay. So here are some examples of method. And first one is known as free method, and here the independent sets are all subsets of E. And if independent sets are if independent sets are all subsets of E of some size less than equal to K, then we call it a uniform method. And the third example is a method from linear algebra. Let E be a finite subset of a vector space, and we define a metroid on E by taking the independent sets as linear independent subsets of E. For example, we can take E as the columns of a matrix. So now, instead of taking linear independent subsets, if we take the independent sets as the basis of column space of A, then it satisfies these additional properties. And this is known as symmetric exchange axiom. And if a for a finite set E and family of subsets of E which satisfies this axiom, these two together is called delta method of G. Here the subsets are called feasible sets, and this the delta method was first introduced by Bruchet in 1987 as a generalization of method. And a delta method is a method if the feasible sets all have the same cardinality. And here is an examples of delta method. So like if you take a symmetric or skew symmetric matrix of size n, and you define the feasible set F is as follows. Take F is a feasible set if and only if the determinant of principal submatrix of A corresponds to F is non-zero. And Bruchard shows that with this system, this provides a delta method, and which is called as a linear delta method. Now the question is, so far we have discussed about real, stable polynomials and delta methods. Is there any connection between these two notions? And this was a result by answer is yes, and this was a result by Brandon from 2007. So given a real stable multi-affine polynomial, the set of monomials in P forms a delta method with this ground set. Now remember that our blow-up polynomials is real stable and multi-affine. Thus from PG, we can obtain a delta method, and in fact far more risky, this delta method is linear. And we call that as blow-up delta method and denoted by MMG. Now look at this blow-up delta method for G as a path graph on 3 nodes. This is exactly same as this. Now, here this coefficient here the coefficients of monomial of third degree is 0 because this is a blow up of an edge, and this is also infeasible because this is a copy of a same vertex. Now the question is, also more generally, one can verify this. This inequality holds for small path graphs for path graphs pk for small values of k. Now the question is, does this inequality holds for all values of k, or an independent of 1? Does this right hand side delta side is a delta method for all k? And here is our result. The right hand side, this right hand side is indeed a delta method for all k, and it is equal to a blow-up delta method if and only if k less than equal to 8. By explicit calculation, one can show that this is not a feasible set for a delta method on blow-up delta method of path graph for k greater than equal to 9. So in particular, for k greater than equal to 9, this left hand side is a proper subset of the right hand side, and this right hand side gives a different delta method. Now the question is, can this right hand side delta method generalize to more general graph? And this turns out to be hold for tree. And okay, how much time have you? Okay, so okay, I'll maybe skip this. Okay, so here is our okay, I'll just so now just look at this. I'll explain why this is an infeasible set. So this is an infeasible set because this is a blow up of an path graph. So it's coefficient. So the coefficient in the of third degree, in the coefficient of ni plus 1, ni plus 2 in the blow up polynomial is 0. So more generally, if we take any tree containing 2 leaves with common parent, is a blow up. Now, if we set all such subsets of nodes to be infeasible set, does this gives a delta method? And answer is yes. So before this, we need a basic definition. So recall that a Steiner tree Ti of a subset of vertices I is the of tree is the unique smallest subtree containing I. So suppose T is a tree, and define a subset of vertices I to be infeasible if the Steiner tree Ti has 2 leaves which are in I and have the same parent. Then the remaining feasible subsets form a delta method. And okay, so we provide a novel delta method for each tree. And we show that that construction of this delta method does not extend to for more general graphs. So now there is a potential question: is there any connection between these two delta matrices to any other known delta matrix, any other known combinatorial delta matrix? So, and here is the archive link for the full paper. Thank you.
Thank you very much. There are questions.
Hi, thanks for the great talk. I was curious about your blow-up polynomials. You write them as the determinants of these sort of ever-growing matrices. Is there a formula for your blow-up polynomials in terms of as the determinant of like a linear matrix in your N1 through N?
Yes, yes, there is a formula. So we defined a modified distance matrix, something's called. So which will be a distance matrix, and in the diagonal, instead of 0, we put 2. Like all the diagonal entries will be 2. So using this, we defined a so this suppose this blow up of each vertex is N1, N2, N1. Okay, so the determinant of this blow up is determinant of I plus I think this modified distance matrix times, if we define this as a diagonal matrix with this diagonal entries N1, N2, Nk times this.
What's N?
This N is a diagonal matrix whose diagonal entries are N1, N2, Nk. And these numbers are the like we blow up the each vertex. Like N1 is blow up with a N1, first vertex is blow up with an N1 different copies. Similar. Yeah, or M is a like this D is a distance matrix plus a diagonal
This might so this determinantal formula actually might give the sort of interlacing, might give you some of the nice interlacing that was asked before. It's great. Thanks.
So this distance matrices, can you add some weights to the edges? So you get like a weighted version of this.
Yeah, so we proved this result in this result we proved in full algebraic. Even like we can put a weighted, we take weights from a arbitrary commutative ring also.
And do you get stability in that setting also for like real positive weights?
Can you repeat this?
Do you get stability, this real rootedness for when you have the weighted version of the?
Yes.
Oh, nice.
This metric spaces.
Is there a further question?
Thank you. Very nice talk. I was wondering if I hand you a polynomial, can you tell if it's about a blow-up polynomial of a graph?
Sorry?
If you're given a polynomial, is there a straightforward way to tell if it's a blow-up polynomial of a graph without testing all graphs of the right size?
Yes, so if we get so the polynomial must be multi-affine and real stable, and from this I think we can construct a graph.
You can construct a graph.
Yes.
Yeah.
So I was wondering if there's, so I mean, since there was this discussion on, you mentioned deletion contraction, I was wondering if, and this polynomial is multi-affine, if there's any relation to multivariate Tut polynomial which is multi-affine in some of the variables.
Multi-affine in.
So there's a multivariate version of the Tut polynomial due to so-called.
Okay. So I think he may ask. I don't have an idea.
Thank you.
So it seems that all questions have been answered for the moment. So let us thank our speaker again. And don't run away because there comes some announcements.
Thank you. So I hope all of you are getting ready to go to the banquet tonight. If you have changed, so we have about 100 plus epsilon people participating. 100 people can squeeze into exactly 2 buses. So if you have decided not to go to the banquet, please let me know ASAP. Otherwise, I'll have to arrange another small bus. So if you are planning to go to the banquet, no need, and have signed up, no need to do anything. If you have signed up and have suddenly decided not to go to the banquet for whatever reason, please let me know very soon. No, we can arrange another one. So yeah. So there is alcohol available at the banquet, but we are not allowed to pay for it. This is some Indian government rules. So you can purchase alcohol at the bar over there at your own cost. And that's perfectly fine. So considering this last point, I wanted to know if it's okay if we leave a little early. So the last talk of the day ends at 6 p.m. Is it okay if we leave at 6:30 instead of 7? I mean, all conversations we can continue in the bus and over there with alcohol. Maybe, as Sarah has told me, alcohol makes all conversations and talks more interesting. So, so is it okay if we leave at 6:30 instead of 7? Is that fine? Does anybody object? Okay, so so the bus will be at the same the buses will be at the same location as they were yesterday, behind the main building, and we will plan to leave at 6:30. Okay. All right. So let's break for coffee.
Send an email to all participants. Yeah. Okay. Anyway, information because some people. Hmm?
What if he joins like a time? Give him.
So we have a small or bigger problem, depending on how you see it. The speaker has not joined yet. Okay, so unfortunately, speaker still is not here. So I propose that we liberate you. That is, you are free to do anything you like. And in case speaker shows up, then I will get you back in. And if not, then we have the next talk at 11:30.
So well, since I have time, I make some more announcements. So, cause and effect. So Indian participants from outside Bangalore, please do fill up the TA forms and submit by tomorrow. This is very, very important. Yes? No, you can email them. Yeah. So, but please do collect the TA forms and fill them before Friday. This is urgent. And okay. And we will have another group photo session for those who are here in the second half, just before lunch. So when this session ends. Yes. Yeah, I was going to propose that. So Tom Roby sent me the link to his photos from yesterday's trip. I suppose some of you have also. So Tom, could you open up the album to other people to add photos? Is that okay? So maybe I'll forward the link to Tom's album, and anybody who feels like can add their own photos of pouring rain. No. Yes. That's yellow. The raised hand is yellow. Yes, Sheila. Yes. So I will send an email about that. So we will put up the slides for the talks with permission of the speakers. For those of you who have already given the photos to Atul, we have them, and if it's okay, we will put them. I'll send an email again requesting permission. And for the posters, we already have received most of the posters from people who wanted to send them, so we will post them as well. Yeah. Anything else? Okay. So we can disperse and come back later. Yes. Good. So the plan, thank you, Michael. So the plan for Friday, again, this is completely open to anyone who wants to join. So after the last talk of the day and of the meeting, maybe we give ourselves half an hour, and then we take a walking tour through Malleshwaram, which is in the south of the campus. At least for those of you who are not from India and are interested to see how, and are interested maybe in purchasing something for your near and dear ones, or also for the cultural experience of going through a crazy Indian market, crowded. We walk through and also seeing a flower market. This is something maybe you've not seen. We'll walk about 3 kilometers or so, and we'll end up at a very nice sweet store. So you can buy, and we have something to eat there, and maybe also it's a very good quality store, and so if you want to take something back on your flight, you can also purchase something from there. So also savories, not only sweets. So the plan is to take a walk, and those who want to come can come. Don't want to come, it's okay. We'll decide the precise details. Sorry. So the talk will end at 5. So around 5:30 we leave, and it'll be a walk, and then we walk back. Yeah. Tomorrow. This is the last thing, social event or whatever. Yeah. That's posted on the web page. And remember, there's the concert on Saturday again for those of you interested. It's like I'm giving the talk. Sure, with pleasure. So they are removing the poster boards. So if you have your poster over there, it would be good if you could remove them. Otherwise, we will remove them and place them in the ante room. You can collect them later.
Okay. Can you hear me? Perfect. Okay. Let's see.
So our next talk will be given by Sophie Rehberg. And she is going to explain rational Erhard theory to us.
Yes. Thank you. First of all, I would like to thank the organizers for this nice event that we are enjoying this week and for the opportunity to speak here. So this is joint work with Matthias Beck and Sophia Elia, and I will try to give a two-slide summary of what Erhard theory is, and then as a motivation to what's new, why do we do rational Erhard theory and what's happening there. And then in the end, I will give an example of a concept that carries over. I will talk more about this later. Okay, so we have seen Erhard polynomials a couple of times this week. Nevertheless, let me define them again. So we are thinking about polytopes. Those are convex halls of finitely many points in some space. Our polytopes in this talk are always full dimensional. And then we are interested in counting lattice points in those polytopes, so points with integral coordinates, and also counting them in any positive integral dilate of the polytope. And we define this counting function, this Erhard counting function that I've written there. And then here's an example, the unit square, and you can easily figure out that the counting function is n+1 squared. So that's a nice polynomial, and that's no coincidence. That's a theorem by Erhard from the 60s, that whenever you have a polytope with integral vertices, meaning all coordinates have integer values, then this counting function agrees with a polynomial of degree d. And that's why we call it Erhard polynomial, because it actually is a polynomial. And then you can generalize this to polytopes that have rational coordinates. And the counting function is still somewhat nice. It's a quasi-polynomial. And a quasi-polynomial looks like a polynomial, but the coefficients are now periodic functions. Yeah, instead of constant coefficients, we have periodic functions. And then we can give a bound, or can somehow estimate what the period of those, the common period of those coefficients is, by looking at what we call the denominator of the polytope. And the denominator is the lowest common multiple of all the coordinates of all the vertices of the polytope, right? So it somehow measures how rational are the vertices of the polytope. And then the period divides this denominator. Okay, and then of course, we want to do formal power series. Right? So we throw this into a generating series. And we can see that this is a nice form as a rational function. We know what the denominator looks like, and the denominator is called the H star polynomial. That's again a polynomial with non-negative coefficients, with non-negative integral coefficients. Okay, so here's a crash course in how to compute the Erhard series for simplices. Yeah, we have this interval from 1 to 3, and what we do is we place the polytope in a vector space 1 dimension higher at height 1, and then we look at the cone over it. Yeah, so I've placed this interval, where am I here? At height 1 in this 2-dimensional space, and then I take the cone over it. And then in order to compute the H star polynomial, the only thing we have to do is we look at this half-open fundamental parallel pipette spanned by the generators of the cone. And we look at the integer points in this half-open fundamental parallel pipette. And then this 0 point here gives us a constant 1. this point at height 1 gives us this t. And if there were, let's say, 3 points at height 2, we got 3 times t squared in this polynomial. Yeah, so we look at the number of points at each height. Okay, are there any questions so far? Let's take my 2-slide summary of Erhard theory. Yeah, only in the interior, because we make it half open at the top, right? So those points are not included anymore. We take out the upper facets. Yeah. All right, so now I will move on to what we want to do now is, instead of only considering integral positive dilates of our polytopes, we want to consider rational dilates. Or actually, we can even consider real dilates. We will see that it doesn't make any difference. And of course, we were not the first ones to think about this. So there's a very nice paper by Eva Linke, who studied this counting function, and she already shows that this is a quasi-polynomial again, and that the coefficients are piecewise polynomial, and they are related by derivatives and many other nice properties. There's a paper by Baldoni, Berline, Körper, and Vergne, who studied intermediate sums, and we can see this counting function there as a special case. And then Stapleton and some papers already introduced some kind of generating series approach, but he was counting integer points on boundaries of polytopes that always contain the origin. And we will also see that in the rational world, this will be a special property. Yeah. Okay, so let's get started with definitions. So we again define this counting function in the way you would expect it. Instead of taking integral dilates, we now allow rational dilates. And again, we could also allow real dilates. It doesn't really make a difference. So let's look at some examples. Very easy example, unit interval. We again place it in the space 1 dimension higher and look at the cone over it. And now what we one nice thing that I didn't tell you about this cone picture is that we can recover the polytope by intersecting the cone at height 1, right? And we can also recover dilates of the polytope by intersecting at different heights. So if I intersect at height 2, I get twice the polytope back. So now what we can do is, like, if we can intersect this cone at any height and see how many lines over integer points do we have in there. And that's what we actually want to count. Right? And then you can figure out we just need to take the floor function and add 1. And we can see this is a quasi-polynomial. It's a monotone function. That's everything we would expect. Okay, here's the second example. We take the interval from 1 to 2. And now things already get interesting. This is still a quasi-polynomial, but if you look closely at it, the original polytope contains 2 lattice points, 2 integer points, 1 and 2. If I now dilate it with a factor that's slightly bigger than 1, let's say 1.2, I will only have 1 integer point, right? You can see this in the picture here. If you go slightly higher, this line exits the cone. This one is in there, but the next one is not in there yet. So this counting function is not monotone anymore. And also, if you think back to the example before, it's just a simple translate, right? So I've just shifted this interval by 1, and it changes its properties. So that's something people who are used to classical Erhard theory, everything is invariant under integral translations. So I used to think about polytopes in terms of their shape and their size, but never in terms of their position. But here it actually really matters the position where the polytope is located. Okay. So now we are somehow stuck with this continuous counting function, but actually what we are doing is we are still counting discrete data, right? We still are counting integer points. So only at certain points when I dilate, something happens. Yeah, for some intervals, this counting function is just constant because, well, we need some time to reach the next integer points. And we can explain those intervals by introducing a new parameter that we call the codenominator. Let me explain what this is. So now we need to look at the half space description of the polytope. So every polytope can be described in terms of the intersection of half spaces. And that's this system of inequalities there. And now we want to say we only consider rational polytopes. So we can write this description with integer matrix A and an integer vector B. And then I also require that this description is in lowest terms, right? So every row of A and B together is in lowest terms. And now, since the polytope is also full dimensional, this description is unique. And then we can define the co-denominator as the lowest common multiple of all the entries in B. And this is well defined. Okay, let's look at our examples again. Here's the half space description of this interval, and then the co-denominator is 1. And for the second interval, the co-denominator is 2. And this co-denominator gives us the intervals in which this counting function is constant. And that's the first proposition here. So if we have a polytope, this counting rational Erhard counting function is constant on open intervals from n over r to n plus 1 over r, where n is a natural number. And then if the polytope contains the origin, we've seen in the example, and it's true in general, that then this counting function is monotone, and we can close the interval on the lower bound. And that's nice. That's why we don't really care whether we want to do rational dilates or real dilates, because we only have to look at some intervals. And we are back to looking at actually discrete data again, right? And now we can define rational Erhard series and refined rational Erhard series. So for a polytope that contains the origin, if I want to know all the data of like every dilate, actually I only need to know the values of this counting function for multiples of 1 over r, right? Because then it's constant, and then I have the next multiple of 1 over r. And I can define a rational Erhard series by just using those data, and I will have everything, all the information that I need. And then if the polytope doesn't contain the origin, well, I need more data, right? I need the endpoints of all the intervals. So I still need all the multiples of 1 over r. And I need some value in this open interval. It doesn't really matter which one because it's constant. So we just chose the midpoint, because then we can write the refined rational Erhard series as like collecting all the data, like all the values for multiples of 1 over 2r. And then we have all the information that we need. Okay, so now let's study these Erhard series, these rational Erhard series. Here they are again. And here's our first theorem. We can again write them in a nice rational function form. Yeah. So we always assume P is a rational polytope of dimension D, so full dimensional. The co-denominator will always be called R. And then we have one extra parameter that we call M, such that M over R is again a lattice polytope, meaning a polytope with integral vertices. And there are at least 2 canonical choices for M. I will talk about them in a couple of slides. And then we have this nice form. We have again a polynomial as nominator, which we call the rational H star polynomial, which depends on M. And it has again non-negative integral coefficients, but it is a polynomial in t to the power of 1 over r. So we now have fractional exponents, as we also might have in the denominator. Yeah. Okay, let's look at an example again. Oh, and we can do this again for the refined rational series as well. This will always happen. Whenever we know something about the rational Erhard series, we just replace r by 2r and rh star by double rh star, and the same things work. Yeah, it's the same, kind of the same thing. All right. Oh, yeah, I wanted to show you the proof because it's easy, and it tells us how to compute those Erhard series and Rh star polynomials, because you can just like reduce it back to classical Erhard series, right? So here's the definition of the rational Erhard series. And then what we do is we dilate by n over r, but that's the same thing as first shrinking the polytope by 1 over r and then dilating by integral parameters n, right? So we can rewrite this again and apply the classical Erhard theorem, and we get this nice expression. Yeah, so it heavily relies on the classical result. And that's how we can compute the rational H star, as we will see here in this example, right? So we've seen what we do actually is we compute the Erhard series for 1 over 2r in this case of the polytope, right? So in this case, R is 2, 1 over 2R is 1/4. So we shrink the polytope by 1/4, embed it at height 1, and then look at the cone over it. There's a different picture, which I like much more because it's easier. We can just rescale this additional dimension, and then we get this picture, which is much easier to look at. And now we don't look at integral heights, but at heights that are, again, multiples of 1 over 2R, right? And now we can read off the RH star polynomial, right? So we have, here we are. We have 1 point at the origin, which gives us this constant 1. We have 1 integer point at height 1/2. So we get t to the power of 1/2. We have 1 point at height 3/4, t to the power 3/4, and 1 at height 5/4. And we get this. And that's it. All right. And then we can do like usual generating function knowledge. We can apply that here, and we can see that this counting function actually is a quasi-polynomial again. And we can again give an estimate on the period. It has a fractional period, j over r, and j divides m, right? M was this parameter that we choose here so that m over r times the polytope has integral vertices. So in that case, we want to choose m as low as possible so that we get a nice bound on the period. So the smaller the period, the simpler the counting function is. So then we know like how complicated, we better know how complicated the function is. Okay, we can also do reciprocity, and those things were already in the paper by Eva Linke. We can recover this here. And we can also, in the case that m over r is again an integer, which is the second canonical choice for m, we can retrieve the h star polynomial from the RH star polynomial by just looking at all the summands that have integer exponents. Yeah. So here's the example from before. If you just take the summands with integer exponents, we are left with 1, and that's the classical Erhard series of this simple interval from 1 to 2. All right. Are there any questions about this so far? The setup, the definitions, the series? All right, so now we have a rational Erhard series, and we can ask many questions from classical Erhard series, how they carry over in this new, like, refined world. And I want to show you this in the example of Gorenstein polytopes. I will define what they are and why they are nice, and then we will see how we can generalize this into a rational Gorenstein polytope definition. Okay, for that, we first need the definition of what a Gorenstein cone is. That's a pointed cone, where we can find a point so that if we translate the apex of the cone to that point, this new cone still captures all the interior lattice points of the original cone. And then this point is called Gorenstein point. Yeah, so you can see this in the picture here. We have this cone, and then we have this point here at 1, 1. And if we move the apex of the cone there, this new cone still captures all the interior lattice points of the original cone. And then we call a lattice polytope a Gorenstein polytope if the cone over the polytope is a Gorenstein cone, right? This construction of putting the polytope 1 dimension higher and coning over it. So why is this nice? Here's an example. Those polytopes, they have some dilate where we have a unique interior lattice point. And the H star polynomial of such polytopes is palindromic, meaning if I read the coefficients from left to right or right to left, it is the same thing, they're symmetric. Yeah. So here's this triangle, which is one example. And if you see, if you dilate it by 3, you get this bigger triangle with a unique interior lattice point. Okay, and now we generalize this to gamma rational Gorenstein polytopes, where we say, well, a polytope is gamma rational Gorenstein if the cone over the 1 over gamma times this polytope is a Gorenstein cone. Why do we introduce this parameter gamma here? Because we need to do this for R and 2R. And we can do this for other parameters as well. We are not sure whether this tells us something interesting. But anyway, it's easier to state the definition with some new parameter. But you can think of gamma as always being R or 2R. Yeah, and then it's easy to see that a lattice polytope is Gorenstein if and only if it's one rational Gorenstein, because if we replace gamma by 1, that's just the definition from the slide before. Okay, here's our favorite example again, and we can see it is 2 R rational Gorenstein, meaning here it's 4 rational Gorenstein, right? We have this point here where we can translate our cone, and this cone captures all the interior lattice points that we are interested in. And we can also see again that this RH star polynomial is palindromic. Well, here all the coefficients are 1, so it's a little bit boring, but in particular they're palindromic. And that's a general phenomenon. Yeah, so also for rational Gorenstein polytopes, we have this characterization. Yes, a bunch of them. So if we have a polytope that's R rational Gorenstein with this Gorenstein point, then this point gives us a unique integer solution to the system of equations. The RH star polynomial is palindromic. That's another way of writing it. This is a way of writing this in terms of the Erhard series or the counting function using reciprocity. And this last equivalence is actually well known in the literature. We just have it in the theorem because we need it in the proof. And of course, we can do the same thing again for, this was for polytopes that contain the origin, right? And then we can do the same things for polytopes that don't contain the origin by replacing R by 2R. And we get the same equivalences. Yeah. Okay. And we could actually write down these theorems for any L times R Gorenstein. We just don't think it tells us anything interesting, but it's possible. Okay, let's look at some examples again. Here's a different interval, slightly more complicated, from -1 to 2/3, and then the RH star polynomial looks like this. And if you stare at it for a moment, you can see that the coefficients are palindromic. You can also see that this is already pretty complicated for just being an interval in 1 dimensions. And it demonstrates a general phenomenon. Whenever we have the origin in the interior of the polytope, as it is the case here, then the polytope will be R rational Gorenstein with this Gorenstein point at height 1 over the origin. So this is again telling us the location of polytopes is very important, because in general, like in the classical world, a polytope being Gorenstein is a super special property. And here, all the polytopes that contain the origin in their interior, they are rational Gorenstein. So this is a super special property if a polytope contains the origin, because we cannot just translate polytopes. Okay, here's the second example you might recognize from a couple of slides before, which is this triangle, but now slightly bigger from 0 to 2. And this is actually rational Gorenstein. You can see this in this RH star polynomial here, but it is not in the classical world, because now if I dilate this polytope by an integer dilate, I already get 3 interior lattice points. Yeah, but there is some dilate that contains a unique interior lattice point, which in this case is, I think, 3 halves, right? So then we get the same thing back. So with rational Erhard theory, we are able to somehow recognize that this polytope actually wants to be Gorenstein, right? It has a smaller dilate, which is Gorenstein, and we can see that here. And we can also see that, right, we can recover the H star polynomial from the RH star polynomial by looking at the summons with integral exponents. So this is actually refines this, and then it's symmetric or palindromic. Okay, but not all polytopes are rational Gorenstein. Here's an example of a polytope that's not rational Gorenstein. We've computed the RH star polynomial here. You can see it's far from being palindromic. And you can also see that in the picture. If you dilate these 2 interior lattice points, they enter and exit the polytope at the same time. So we will never have a unique interior lattice point. All right. So now we can, as I said, look at many other questions that we know from classical Erhard theory. For example, it would also be interesting to look at what does it mean to be reflexive in the rational setting. In the classical world, reflexive the Gorenstein polytopes are a generalization of reflexive polytopes. Reflexive polytopes are those that contain a unique interior lattice point. And then if you look at the polar dual, this polytope is lattice again. And they have a bunch of other interesting properties. But it's not so clear how to do this in the rational setting because those properties do not always coincide. There might also be connections to the fine interior of lattice polytopes. This is also a way of defining, like generalizing the notion of reflexive. There's also a bunch of generalizations of reflexive polytopes already. And really, we can ask any other theoretic questions about unimodality of RH star polynomials, log concavity. We've heard these things. All right, thank you for your attention, and I'm happy to answer more questions.
Thank you very much. Are there questions?
Interesting. Okay. Thank you for that lovely talk, Sophia. It's always exciting to hear you speak. Do you know this last point you said, any other Erhard theoretic question? Have you all thought about symmetric decompositions of the rational H star?
I have not, but Esme Bajo and Matthias Beck have. They recently posted a paper about symmetric decompositions, where they also consider the rational H star. So there's a paper on arXiv where you can read about this. Yeah.
Another question?
Hey, thanks for the talk. So maybe a basic question, but like when you talk about the cone, you use this Hom notation. So is there some connection to algebra there? Like, is this the same as the Hom set from algebra?
It's also called homogenization, because if you look at the description in terms of the intersection of half spaces, you will get a system of inequalities where the right-hand side equals to 0, because all the hyperplanes then go through the origin. So it's a way of homogenization of your system of inequalities.
So for some rational polytopes, you can still have a period collapse. That means that you still have a polynomial, Erhard polynomial. So that's something you can detect with your rational H star polynomials.
Thank you so much for this question. I have an extra slide for this because we also thought about this question. So let me get everybody on the same page. Period collapse means whenever we have this upper bound on the period by the denominator, and whenever we actually have a smaller period, we call this period collapse. And this is a very weird phenomenon that's like not really clear when it occurs. And here are 4 examples that show that apparently there's no relation between integral period collapse and rational period collapse. So here's one classical example where we have integral period collapse, but no rational period collapse. Here's a recent example from a paper where we have integral period collapse and rational period collapse. Here's a simple example where we have no integral period collapse, but we have rational period collapse. And in this example, there's no period collapse at all. So yeah, we were also hoping to see something there, but we have this kind of non-result.
More questions?
Might just be nothing, but one of your examples had 1 minus t cubed in the denominator. And I just noticed that if you wrote it as if you wrote numerator and denominator as a polynomial in t to the 1/2, that then you have cancellation. Is that something that generalizes? So you just get 1 over 1 minus t to the 1/2 cubed.
Yeah, this somehow boils down to the question or to the detail of how we choose this parameter m. Right, there are several choices of choosing m, and I think here we chose m in a way that m over r is an integer again, because then we can recover the h star polynomial, but you could reduce this expression. Yeah, this expression is highly non-unique. It always depends on this parameter m.
Okay, Thank you.
So no further questions. That seems to be the case. So thank you very much again. All right. I want to remind you, there is the second group photo coming up right now.
Check.
Hello, Daniela. Do you hear me? Can you hear me? Uh, I don't think so. Daniela, welcome.
Yeah.
Yes, do you hear us?
Hello.
Hello.
Yeah, I can hear you. Yeah.
So, I think we can hear you very well. Yes?
Um, can you
Uh, sorry, could you say something, please, so we can check the sound, please?
can you hear me now?
I think it's okay. Some more?
Okay.
I think it's okay, yes.
Good.
Good. Can you hear me?
Yeah, I can
Yes.
hear you very well. Yeah.
Yeah. Okay. Wonderful. So we will start soon. We'll wait. Some people will arrive still after
Okay.
the lunch, and so when we'll arrive in several minutes. Daniela, could you please share your screen with us?
Yeah, of course.
Thank you. It works well. Perfect. We'll start in 1 minute now. Everybody are coming.
Okay.
So aren't we probably should start, yes? We should start probably, yes? Okay. So hello, everybody. Now we start our afternoon session. And for the invited talk, we are very fortunate to have Daniela Kuhn from the University of Birmingham. And she will tell us how she and her team proved a conjecture about graph coloring that existed half of the century before. Please go on, Daniela.
Okay, so thank you very much for the invitation. So the talk is about the Erdős-Faber-Lovász conjecture, and it's joint work with Yap Kang, Tom Kelly, Abhishek Mechuku, and Derek Ostos, all of whom are at Birmingham. So the Erdős-Faber-Lovász conjecture is a conjecture about graph colorings. And this means that you have a graph, and what you are doing is you color the vertices of this graph. But the property you want to achieve is that whenever you have two vertices which are joined by an edge, then they should get different colors. Okay? And the chromatic number is just the minimum number of colors with which you can do this, and it's denoted by chi. And now what does the Erdős-Faber-Lovász conjecture say? It says that if you have a sequence of graphs, of n complete graphs, such that each of these graphs has at most n vertices, and such that whenever you look at two of these graphs, they intersect in at most one vertex. Then you can color the union of these graphs with n vertices. So if you look at this picture here, we have one graph which consists of 4 complete graphs. And each of these complete graphs has size 4, and we have colored the union, the entire graph, with 4 colors. Okay? Now, Erdős-Faber and Lovász, they actually formulated this at a tea party at a conference in Boulder. And at the beginning, they thought this is some toy problem, and they should be it should be easy to solve. So they expected it to be solved in the afternoon, or at the very least on the next day. But it turned out to be a bit harder than they thought, and so Erdős actually offered an increasing amount of prize money for the solution of this conjecture. So starting with $50, and he raised it in the end to $500, and he actually wrote that he considered this as one of his three most favorite combinatorial problems. And what we did is we proved this conjecture for all sufficiently large n. Okay, now there's also a more general version. Again, you have n complete graphs, and each of these complete graphs has at most n vertices. But this time, whenever you look at two of these complete graphs, they can intersect a bit more. So you're only restricting yourselves to the property that the intersection is at most n t vertices. And then the question is, again, you want to color the entire graph, the union of all these complete graphs. And the question is, how big can the chromatic number be? So this is due to Erdős, and the Erdős-Faber-Lovász conjecture would deal with the case when t is 1. And it would, the answer there is conjectured to be n. Okay, and we proved that if t is not too big, so if t is at most square root n, then the answer is t times n. And this is tight, because there are infinitely many examples where when you look at the union of these graphs, what you get is one big complete graph on Tn vertices, and then of course its chromatic number is Tn. And now this only works if T is at most square root n, but actually this is not a real restriction, because some earlier result of Horrocks and Tusa shows that after this, the chromatic number of the union of all these cliques doesn't grow anymore. So it's always at most n to the 3 over 2. Okay, so basically this settles this question of Erdős again for large n. Now, I formulated this Erdős question, also the Erdős-Faber-Lovász conjecture in terms of graphs. But it turns out that if you work on it it's helpful to think of this conjecture in terms of hypergraphs. So actually, this conjecture has a version in terms of a reformulation in terms of hypergraphs, which I want to show you. But before I do this, I would like to introduce some terms about hypergraphs, because obviously we need them. Now, if you have a graph, you have vertices, and some of these vertices are joined by edges, so every edge has size 2. In a hypergraph, you allow the edges to have size also bigger than 2. So, for example, if you look at this picture on the right here, every edge has size 3. Okay? So all these things here are hypergraphs. In particular, a graph is a hypergraph. Apart from the fact that the middle one is a multi-graph, and so this is a multi-hypergraph. So multi-hypergraph is just a hypergraph where you allow multiple edges. Now, if every edge of your hypergraph has size k, then we call it k-uniform. So if you look at graphs, then these are 2 uniform hypergraphs. And if you look at this thing on the right, every edge has size 3, so it's a 3 uniform hypergraph. And the last thing we need is the notion of a codegree. And this is, well, you look at any 2 vertices in your hypergraph, and then you count the number of edges containing these 2 vertices. That's the codegree of this pair. So if you do this for graphs, where you don't allow multiple edges, well, then any 2 vertices only lie in at most 1 edge, and so the codegree is 1. But for hypergraphs, you can get bigger codegree, of course. Okay, and we will be talking about edge colorings of hypergraphs, not vertex colorings. And so we also need to talk about matchings. Now, a matching is just a collection of edges which are pairwise disjoint. So you don't want to have edges which intersect in 1 or more vertices. Okay, and an edge coloring of a hypergraph is when you give the edges of your hypergraph colors. But the property you want to guarantee is that whenever you have 2 edges which are not disjoint, then they should get different colors. And so this means your task is you have to look at the entire edge set of your hypergraph, and you want to split it into matchings, because then every matching you can color the same. And so you have an edge coloring of your hypergraph. Okay, and the chromatic index is just the smallest number of colors with which you can do this, and we denote it by chi prime. So this picture here shows you the Peterson graph and an edge coloring of the Peterson graph with 4 colors. And if you think about it, you can't do better. So its chromatic index is 4. Okay, so if we only look at edge colorings of graphs, then these are in some sense very well understood. For example, we have this old theorem of Wiesing, which tells you that if we have just graphs, then the chromatic index is either the maximum degree or it's the maximum degree plus 1. So obviously it's at least the maximum degree, because if you look at a vertex and all the edges at this vertex, you have to color them differently. And the theorem says that you can always color all the edges with at most 1 color more than this. Okay? So sort of graphs are well understood, in some sense at least. Hypergraphs are harder. So if you look at the picture, we have a coloring of this hypergraph, which you probably can't really see. So we have 2 purple edges, 2 blue ones, and 2 green ones. Okay, but in general, the problem is hard. So even finding the largest matching in a hypergraph is NP hard, and this is in contrast to graphs. Okay, and here's the promised reformulation of the Erdős-Faber-Lovász conjecture in terms of hypergraphs. And this is about linear hypergraphs. And linear hypergraphs are hypergraphs of codegree 1. So remember, this means that whenever you look at two edges, either they are disjoint or they intersect in precisely one vertex. So you don't want to see edges which intersect in at least two vertices. So you have to forbid this. And then the conjecture says that if you have a n-vertex linear hypergraph, its chromatic index is at most n. So you can color all the edges with at most n colors. So Wiesling's theorem actually implies this conjecture for graphs, because remember, Wiesling's theorem tells you you can always color the edges with at most the maximum degree plus 1 many colors. And the maximum degree is for a graph always at most n minus 1. And so you can color the edges with at most n colors. Okay, now I will explain why the graph formulation of the conjecture and the hypergraph formulation of the conjecture are equivalent in a minute. But before I do this, let me give you 3 families of extremal examples which show that the conjecture, if true, is tight. So you can't improve the n here for the chromatic index. And the first class of extremal examples are pictured on the left here, and these are complete graphs on an odd number of vertices. So why is that? Well, you have n vertices, all possible edges in between, each of size 2, so you have a complete graph. So there are n choose 2 edges. Now, if you can color them with less than n colors, well, then every color class is a matching, but it must be perfect. So it must cover all the vertices. And this is just because you have so many edges. But if it's a perfect matching, well, then n has to be even. So if n is odd, the chromatic index must be at least n. So it's an extremal example. Okay, the second class of extremal examples are pictured in the middle here. So it's finite projective planes. So you can see a finite projective plane of order 2. And the edges are sort of indicated by the colored lines. So every colored line is an edge. So in particular, every edge has size 3. And so in general, a finite projective plane of order k is one where every edge has size k plus 1, so it's k plus 1 uniform. It's linear, and it's intersecting. So this means that any two edges actually share a vertex. And it happens to have k squared plus k plus 1 vertices, and also that many edges. So it has n edges. All of them intersect, and obviously so you have to give each of them a different color, so the chromatic index is n. Okay, and the third class of extremal examples is pictured here. So it's what people call degenerate planes or near pencils. So again, we have n vertices, and n minus 1 of them lie in the bottom here. And they form one big hyperedge. So there is this blue large hyperedge of size n minus 1. And the remaining vertex sits at the top, and it somehow forms the size 2 edge, with each of the vertices at the bottom. So this is an intersecting hypergraph. So every edge intersects every other edge. It's linear, and it has n edges. And so you have to color each of them with a different color. Okay, so these are 3 sort of classes of extremal examples. And now, why are these 2 versions of the conjecture, or these 2 formulations of the conjecture actually equivalent? Well, in the talk, I only want to show you how you can derive the hypergraph version, so the version at the top, from the graph version, so the version at the bottom. So let's assume that we believe the graph version, and we want to show that the hypergraph version is true. Okay, so we have an n-vertex linear hypergraph, so maybe the hypergraph here on the left. And we will use it to construct a graph. And what we will be doing is just we will look at the line graph of this hypergraph. So every edge of the hypergraph will become a vertex. Okay, so this blue edge of size 3 will become the top blue vertex in the picture of the middle. And for example, blue size 2 edge will become the bottom blue vertex in the picture of in the middle, and so on. Okay, so the edges become vertices. Now we join two vertices if the corresponding edges intersect, right? So for example, you join the blue vertex here with the purple vertex. If the two corresponding edges, which would be this blue edge of size 3 and the purple edge on the left, they intersect, and they intersect, so we join them. Okay. So this gives us our graph, and by construction, edge coloring of the hypergraph corresponds to a vertex coloring of the graph, and vice versa. Okay, now the graph which we have constructed is a union of n complete graphs. And why is this? Well, for every vertex in the original hypergraph, we get a clique. And these cliques here are pictured in the picture on the right. For example, if we look at this clique of size 4 on the left here, then this corresponds to the bottom left vertex in the hypergraph, right? And why is that? Well, at the bottom left vertex, there are these 4 edges, and they pairwise intersect, so they form a clique. And these cliques have at most n vertices, of course, and each of them, every pair of them shares at most 1 vertex, and this is because the original hypergraph is linear. Okay, and if we believe the graph formulation of the conjecture, then the color the graph which we have constructed with n colors, the vertices, and so we can color the edges of the original hypergraph with n colors. Okay. So this is one direction, and I spare you the other direction. Now, there was this more general problem where you intersect your complete graph, you allow to intersect your complete graph in at most t vertices instead of just in at most 1 vertex. So this was this more general question of Erdős. And similarly, as for the Erdős-Fabor-Lovász conjecture, this has also a reformulation in terms of hypergraphs. So what you get is that you have an n-vertex multi-hypergraph that has maximum degree at most n and codegree at most t. And then the question is, what is the maximum possible value of the chromatic index? So these questions are equivalent. And there is the corresponding conjecture saying that the answer should be at most t times n. And here are one class of extremer examples. And these are t-fold projective planes. So basically you take a projective plane and then you take any edge and you, instead of one version of this edge, you add t versions of this edge. So you add any edge t times. Okay, so in the picture on the left, we have a threefold order 1 projective plane. And on the right, I didn't multiply the edges. So it's just a 1-fold projective plane of order 2. But a projective plane has codegree 1, so a t-fold projective plane will have codegree t, and its maximum degree will be t times k plus 1, and this is at most n if t is at most k. Okay. Okay, so we have seen the Erdős-Fabor-Lovász conjecture and a reformulation in terms of hypergraphs, and similarly, we have seen this more general question of Erdős and a reformulation in terms of hypergraphs. Okay, so but what do we know about these conjectures? Well, let's let's just look at the Erdős-Faber-Lovász conjecture. So remember, and let's look at it in terms of hypergraph. So remember, this means that you have an n-vertex linear hypergraph. And so you have to show that the chromatic index is at most n. And remember, linear means that any two edges intersect in at most one vertex. Then it's not hard to see that the chromatic index is at most 2 and minus 3. So basically, you get a conjecture in within roughly an additional multiplicative term of 2. And why is that? Well, order the edges according to their size. So start with the largest edge and the second largest edge and so on. And then now color the edges according to this ordering. So each time you give the edge you consider the, say, smallest possible color which is available. And then if you think about it, when you do this, you will be looking at some edge in your ordering. And then the question is, how many edges intersect this edge which come before in your ordering? And if you think about it, you will see that there are at most 2 and minus 4 of these edges. And so you can always color with 2 and minus 3 colors. Okay. And Chang and Lola improved this to roughly 3 and over 2. Okay, now here are 3 results which sort of relax the parameters. So the Poon and Erdős theorem tells you that the conjecture is true if in addition you are talking about intersecting hypergraphs. And remember, intersecting means that you have any two edges, but you have to intersect in precisely one vertex since our hypergraphs are linear. And then the conjecture is true. Seymour showed that at least you can find a matching of the right size. And right size means total number of edges divided by n. Now, what does this have to do with the conjecture? Well, if you can color all the edges with n colors, well then because every color class forms a matching, at least one of these matchings must have size total number of edges divided by n. And so Seymour's result shows that at least this consequence of the Erdős-Faber-Lovász conjecture is true. And Seymour proved the fractional version. Okay, here are 2 results which heavily use probabilistic methods. Faber and Harris showed that the conjecture is true if in addition you know that every edge has size at least 3, and at most some constant times, some small constant times square root of n. And Kahn proved that the conjecture is approximately true in the sense that the chromatic index is not much more than n, so it's n plus little o of n. Our proof also heavily uses probabilistic tools, and as I said, we proved that the conjecture is true if n is sufficiently large. And we also showed that there holds a stability result, which was actually predicted by Kahn. And this means that if you know in addition that your hypergraph is not too close to one of the 3 groups of extremal examples which I showed you, then you can do better. So let's look at this in a bit more detail. So again, we have an n-vertex linear hypergraph, but we have these 2 additional properties. And the first one is that the maximum degree of your hypergraph is not too close to n. And this forbids that you are close to a complete graph. And it also forbids that you are close to a degenerate plane, because both of them have maximum degree n minus 4. Okay, and the second condition is that if you look at the edges which have size roughly square root n, then you want that the number of these edges is bounded away from n. So it should be a little bit smaller than n, at least. And this forbids you that you are close to a projective plane. And if you have these 2 additional properties, then the theorem tells you that you can do better. So the chromatic index of your hypergraph is bounded away from n. Okay, now let me tell you a little bit about the proof. So roughly speaking, the two main methods are random nibble, and we want to pair this with absorption. Okay, so what do we want to do? Well, we have this hypergraph and we want to color the edges. So we want to split the edge set into n matchings. And roughly speaking, sort of these matchings are more or less built randomly. So we will build each of these matchings in turn, and to build one of them, we somehow randomly edge suitable edges or eligible edges one by one. That's a bit lying, because actually you add small batches, small random batches, instead of adding these batches one by one. But the message is that if you look at these matchings or at our color classes at the end, then a big chunk of it is built randomly. Okay, but it turns out that this is not good enough, because we want our color classes to cover some desired vertices. And they won't do this if we just build them randomly. So each of the matchings which we construct randomly, we will then enlarge a little bit to absorb desired leftover vertices. So basically, in the end, we do some absorption step, which acts like a sponge. So we will absorb a few desired leftover vertices and making the random matchings, which we have constructed before, into our final color classes. So roughly, this is what we do, very vague. So let's make this a little bit more precise. Before we make this more precise, let me mention that one early success of the random nibble method is this theorem here of Pippinger and Spencer, which also has some
Sorry, Daniela, I
consequences.
think we don't hear you anymore. One
Oops.
second. Now it's okay again. Try again,
Okay,
please.
sorry. So one early success of the Pippinger-Spencer theorem, can you hear me?
Yes, yes. Now it's okay.
Of the Pippinger-Spencer theorem, no, one earlier success of the random nibble method is the Pippinger-Spencer theorem, which will have some consequences for the Erdős-Pavlovas conjecture. So let me state it here. So this is about hypergraphs of bounded edge sizes. So you know that every edge in your hypergraph has size at most some constant, some large constant maybe, but this constant is much, much smaller than the number of vertices. Okay, and then your hypergraph has maximum degree at most delta. But what you want is that the co-degree of your hypergraph is small in comparison to the maximum degree. So it should be little O of delta. And the theorem tells you that the chromatic index is not much bigger than delta. So it's delta plus little O of delta. So this is an approximate version of Wiesing's theorem for such hypergraphs with bounded edge sizes, because Wiesing's theorem, remember, tells you that the chromatic index is at most the maximum degree plus 1. And here you have at most the maximum degree plus the maximum degree. And it generalizes Schröder's solution to the Erdős-Hánányi conjecture about the existence of approximate combinatorial designs. This is where he introduced the random nibble method. Okay, now let me state three immediately immediate corollaries regarding the Erdős-Pavlovas conjecture. So let's first look at the first one here. So the Pippinger-Spencer theorem immediately implies that the Erdős-Pavlovas conjecture holds if you know that every edge has size at least 3 and at most some constant k, where k is much smaller than n. And why is that? Well, how large can the maximum degree of a linear hypergraph be? Look at the vertex, look at all the edges at this vertex. Because the hypergraph is linear, well, these edges obviously intersect in your vertex, but otherwise they are disjoint. And because of this, the maximum degree of your hypergraph is at most this thing here. So n divided by the edge size -1, where you minimize this over all the edges. And so if you have that every edge has size between 3 and k, this means that the maximum degree of your hypergraph is at most n over 2. And so Fpsac theorem tells you that the chromatic index is not much bigger than n over 2. So you have that Erdős-Faber-Lovas holds with room to spare. Similarly, if you look at this more general question, so the T version of the Erdős-Faber-Lovas conjecture, this holds if the edges have bounded size. In general, if you only know that the edges have bounded size and you look at the Erdős-Faber-Lovas conjecture, T is equal to 1, well, then you get from the Pipin-Spencer theorem that the chromatic index is not much bigger than n, because the maximum degree is, of course, at most n. Okay. Now, how does our proof work? Well, roughly speaking, the the reason why we have hope at all is the following. So look at any vertex. So either this vertex has low degree or it has higher degree. Okay, so far so good. But if it has low degree, this means that we have somehow flexibility at this vertex, because what we want is we want to split the edge set of our hypergraph into matchings. But if there are only a few edges at our vertex, then only a few of these matchings have to cover this vertex. And so in some sense, we have flexibility. On the other hand, if the vertex has high degree, well, it must look graph-like. High degree means degree close to n. But if your degree is close to n, then most of the edges at this vertex have size 2. This is because the hypergraph is linear, so the edges are disjoint outside the vertex. But as I told you, we know a lot about edge colorings of graphs. So the hope then is that somehow we can deal with this case as well. So this is the very rough sort of reason why we have hope. Now, let's actually tell you what we are doing, and let's only stick to this case when every edge has size 2 or 3 at the moment. So we have a linear hypergraph, but every edge has either size 2 or size 3. And our task is to show that the chromatic index is at most n. Okay, so what we do is we choose ourselves the set of k colors, and k is a little bit bigger than n over 2. And we want to partially color the hypergraph, so we want to color some edges of the hypergraph such that these 3 properties hold. Namely, every size 3 edge should be colored. Whenever you look at the vertex, at least half of the size 2 edges at this vertex should be colored. And every color class covers every high degree vertex, where again, high degree means degree close to n. So let's assume for a moment that we have found such a partial coloring. Then I claim that we actually are done just using Ising's theorem. And this is because, well, look at the uncolored graph. It is a graph because we have colored every size 3 edge, so we only have size 2 edges left. And the maximum degree of this graph, crucially, is strictly less than n minus k. And why is that? Well, if you look at a high degree vertex, well, it's covered by every color class we have built so far, so it loses degree k. And it had degree n minus 1 at the beginning, and now at most. And so it has degree strictly less than n minus k now. And for the low degree vertices, well, it had low degree before, and because of the second property, you can also show that it now has degree less than n minus k. But Wiesing's theorem tells you that you can always color with maximum degree plus 1 many colors, and so you can color the leftover graph with n minus k colors. And so in total, you colored everything with n colors. This is what we want. So this is what we want to do. And as I said, we want to build our color classes by first doing a random nibble and then using absorption. And the random nibble will roughly give 1 and 2. Apart from it will only always almost give 1, but let's ignore this. We have to fiddle around a bit. And we will use absorption to satisfy 3. But because to sort of cover every high degree vertex. Now, I'm lying a bit here because actually you can't achieve this perfect coverage property in general. So for example, if you start with a complete graph, every vertex has high degree. So in order to achieve this perfect coverage property, all your color classes must be perfect matchings. But if n is odd, you have a problem, of course. So we have to aim for something which is a little bit weaker, namely, we call it nearly perfect coverage property. And this means that every color class covers all but at most one of the high degree vertices. And on the other hand, every high degree vertex is covered by all but most one of the color classes. And then if you do the same thing, it still works, but you need one extra color. Okay, and you need some additional ideas to get from n plus 1 colors to n colors. So let's make this a little bit more precise. So we do in a little bit more detail. So first we have to define a set of high degree vertices. This will be U, and as I said, high degree just means degree close to L. Okay, and then we will set aside a random reservoir of edges. And this will contain only graph edges, so only edges of size 2. And we choose it by choosing just every graph edge randomly with probability R. So this will be set aside. And now we aim to color the remaining edges. Using first a random nibble, and then by enlarging each color class into a slightly bigger matching, such that we can achieve this almost or nearly perfect coverage of U properties. So we want to cover all but at most one vertex in U. So here's our hypergraph. On the top, we have the set U. So we will choose a few edges randomly. Some of these might intersect. We don't want them, so we ignore them, but the others we put in our color class. We look at the uncovered vertices, again, choose some of the edges randomly. Ignore the ones which intersect and put the remaining ones into our color class. And we grow our color class like this until we covered almost all the vertices. Okay, but now we have to achieve that our color class covers all but at most one vertex in U. And we do this by using some of the random reservoir edges and Horst theorem. So if U is small, we find a sort of nearly perfect matching consisting of crossing edges, such that together with what we have built before, now all but at most one vertex of U is covered. And if U is big, actually we are choosing the edges inside. But in both cases, we add this small matching to what we have built previously, and this will then be our first color class. And then we choose the second color class by first doing random nibble, and then doing some whole argument using some of the random of the reservoir edges in order to achieve that our color class covers all but at most one vertex, and so on. And this is the proof. Apart from the fact that, as I said, it only works if you have one spare color, one extra color. So how do you get from using n+1 colors to n colors, say in the case when n is even? But you can show that if you really need this extra color when coloring the leftover graph via Wiesing, then your leftover graph is nicely quasi-random. And then you carefully remove a few more edges to make it also even regular. And then you can apply an older result of Derek Ostos and myself, which shows that if you have such a quasi-random even regular graph, which is not too sparse, then it has a Hamilton decomposition. So you can decompose the edges into disjoint Hamilton cycles. Okay, but if n is even, then each of the Hamilton cycles can be split into two perfect matchings. So you have a one factorization. So you have actually a very efficient coloring. And so you don't need the extra color. Okay, so this was what we do if every edge of your hypergraph has size either 2 or 3. And roughly the same thing works if every edge of your hypergraph has bounded size. So size at most one big constant, which is much, much smaller than n. Now, let's look at the sort of other case when every edge has large size. So every edge has size at least some large constant. And here we want to use some reordering strategy, basically. And for this, we need this trivial fact. Look at any edge, and you are interested in the number of other edges which have size at least your edge E, and which intersect it. Because the hypergraph is linear, it turns out that the number of these edges is this quantity here. But because all the edges are large, this quantity is not much bigger than n. So it's n plus little o of n. Okay, and because of this, you can color greedily using the size monotone ordering of the edges to see that the chromatic index is not much bigger than n. Right, so you again, as I told you before, you order the edges according to their size, starting with the biggest one, and then you color the edges using this ordering, and then you are precisely interested in this number here. So you have an edge, you want to know how many edges have come before and are already colored and intersect this edge. Well, they are bigger, and so you have this number, and so you can color the entire thing with that many colors. But that's not good enough. We want to have n there and not a little bit more than n. So we want to find an ordering such that whenever you look at an edge E, less than n edges preceding E, because then you can use n colors in total. And we can show that either there is such an ordering, or we have structure, namely our hypergraph is close to a projective plane, or the line graph of this hypergraph is locally sparse, and then we use some well-known or some existing results at least about colorings and to finish off this case. So either we have our nice ordering or we use existing results because we have additional structure. Okay, so we can color these small edges using random nibble plus absorption and finishing off by Wiesing's theorem. And we can color the large edges using this reordering strategy. Both of them with n colors. So we've colored everything with 2n colors, which is not quite what we want because we want to have n, right? So of course, you have to make sure that you can run these two cases in parallel, or so at least so that they don't contradict each other. So we will first be coloring the large edges via this reordering approach, achieving some additional properties. And then we color the small edges using the same n colors and make sure that we don't have any conflicts with the large edges. And the second phase is what I done, like I explained before, using a random nibble and absorption and finishing off roughly with Wiesing. Okay, so this is all I wanted to say about the proof. So just let me finish with two open problems. First one is a conjecture of Beersch, Furedi, and Meinl, and it tells you that if you have a linear hypergraph, then its chromatic index is at most this quantity here. So what you do is you look at any vertex, look at the edges at this vertex, but you don't count them, but you look at the union of these edges, and you are interested in how big is this union. And then you maximize this over all the vertices. So here's a picture which shows you a hypergraph which has maximum degree 2, I think. So every vertex is in 2 edges, but this quantity is actually 5. So if you look at, for example, the 2 edges at the bottom left vertex, then they span 5 vertices. And so the conjecture would be a common generalization of Wiesen's theorem and of the EFL conjecture. Because for graphs, obviously this quantity here is at most n plus 1, n. And for hypergraphs, no, for the EFL conjecture, for graphs, this quantity is at most the maximum degree plus 1. And for the EFL conjecture, if you look at this quantity, then obviously it's at most n. So it would imply both of them. And the final open problem which I wanted to mention is the list version of the EFL conjecture, which was conjectured by Faber. So basically it tells you that the EFL conjecture is true if you look at list colorings. And list colorings means that for every edge you have a list of available colors of size at least n. And then you have to find a proper edge coloring, but you have to make sure that every edge is colored with a color of its list, in its list. And if you make all the lists the same, then this gives you the conjecture. And another thing which I wanted to mention is that if you look at the methods of Kahn, then you get an approximate version of this. Okay, so this is all I wanted to say in my talk. So thank you very much for your attention.
Thank you very much, Daniela, for this very colorful and very pedagogical talk. Any questions?
Thank you, wonderful. And I wanted to ask, you showed us how the original formulation of the conjecture implies the hypergraph formulation. Could you say something about the reverse implication?
I can say something, but maybe I actually back to the slide with the pictures. Oops. Yeah. Okay, so so I said you wanted to do it the other way around, right? What I explained is happens if we believe the original formulation and want to show the hypergraph formulation. This is what I explained in the talk. So I think you are asking me to do the other direction, or should I explain the direction I did before again?
Yeah, how the hypergraph formulation implies the original EFL.
Okay, so now we So now we are saying that the top version holds, and we want to derive the bottom version. So we are given a graph and somehow want to construct a hypergraph. And basically, the graph is a union of clicks, and every click will become a vertex in your hypergraph. Okay, so you have vertices 1 up to n, say, and now you have to define how you define the edges, and basically every edge of your hypergraph will correspond to an intersection of 2 clicks. So if you look at a vertex which is in the intersection of cliques, well, it will be the intersection of, say, 5 cliques. And then in the hypergraph, you draw a hyperedge consisting of these 5 cliques. Okay, so this is how you construct your hypergraph. So again, the vertices are the cliques, and the hyperedges basically correspond to the vertices in the intersection of cliques. Okay, and now we want to color the edges of the hypergraph. We get from the graph version, we get a coloring of the vertices of the original graph. And so basically we have colored also the vertices in the intersection of cliques. But the intersection of cliques correspond to the hyperedges, so we have colored the hyperedges. And now you only have to check that actually the hypergraph which you are getting is linear, and this is because every 2 cliques only intersect in at most 1 vertex. And it has n vertices, of course, and that's all.
Some more questions?
Just a curiosity, do we have a good idea of for how large a value of n the proof techniques go through? And for small values of n, do we have any pathological examples?
For smaller values of n, we basically only have these results which I showed you. Our proof uses a lot of probabilistic tools, and so you have to make sure that the estimates are going to hold. And the additional sort of results we will be using. So for example, the result which I showed you, which brings you from n+1 to colors to n, actually also use the regularity lemma, so n will be huge. It will be really huge. So we never calculated it, but it's really massive.
Thanks.
Are there other questions? Okay, let's thank Daniela again.
Okay, thank you very much.
Thank you very much. So we will start at 3. We have 6 minutes break. Arvind will make an announcement.
So, is there anybody who, any of the foreign delegates who needs a COVID test to enter your country from India? If so, please let me know. I'll try to arrange one. So I know that some of you do need. So okay, so you too. So Fufa also, yeah. Okay, so 3 of you. You too. So 5. Anybody else? So we'll talk about your flight, and you tell me how many hours before you need it. Okay.
Does this work? Yeah, good. Okay.
Next, let us welcome Fern from the University of Sydney for a talk about the action by separate permutation on the Kazhdan-Lustig basis.
All right, hi friends. If I haven't gotten to meet you yet, I'm Fern. And this is part of work I did with Oded Jacobi, who is my honors supervisor at the University of Sydney. And I want to talk about things we've been thinking about for the last 2 years or so. And this project has sort of like spiraled and developed and had lots of different parts come in that we didn't really expect. And so I want to kind of share all those results with you. So originally this talk was titled Acting by the Long Cycle on the Kazhdan-Lusztig basis, but as we'll see, this kind of extended to a whole other class of permutations. Okay, so this is my first Fpsac, so you're all going to go easy on me. I'm going to do everything finite dimensional, characteristic 0, type A. Okay, so we're looking at the symmetric group. It acts on its irreducible representations called the Speck modules. And so the Speck modules can be indexed by partitions. And usually these have a basis that are sort of typically indexed by standard Young tableau. And in particular, our point of interest is we're going to look at this special basis called the Kazhdan-Lusztig basis. And this has many connections to Hecke algebras and knot theory and Schubert calculus and all sorts of things. But for us, maybe if you haven't seen it before, you can just treat it as a black box. It's some basis for our Speck module that people care about. And traditionally or historically, the difficulty with working with this basis is that it's very hard to compute the action in general. And that's sort of the main drawback, is we don't really know how elements act. You can kind of write down how the generators act, and this relies on the Kazhdan-Lusztig polynomials, which are really tedious to compute. And then for sort of products of generators, it's very, very difficult. But there are two kind of big results in this direction. So the first was proved in a lot of different contexts in the 90s, kind of all at the same time by all these people and more. So you take any partition, so any Speck module, and you act by the longest element. So this is the permutation that reverses everything. Then if you take some Kazhdan-Lusztig basis element, act on it by the longest element, you get another Kazhdan-Lusztig basis, maybe with a negative. So like this is surprising because you have this incredibly complicated generator action and you expand this out with the longest elements, take all these generator actions, but then somehow sort of everything cancels and you just get this. And moreover, if you want to find which basis element you get, you take your tableau T and you apply the Schützenberger evacuation operator. So this is some operator on standard tableau that was already very well known. And it turns out it's kind of exactly encoded, at least up to sign, in this basis. And then in 2010, Brendan Rhodes proved that when lambda is a rectangular shape, so you have this condition, then the long cycle, which is this permutation 1 goes to 2, 2 goes to 3, etc. This again gives you another single Kazhdan-Lusztig basis element. Great. And how do we find it? It's the Jeux-de-Taquin promotion map. So again, there were two already well-known bijections on standard tableau, and they're being encoded in this basis. And if you know some of the history, this theorem of Rhodes was in the paper where Rhodes proves that the cyclic sieving phenomenon for promotion on standard tableau. So this is kind of the main part of the proof. You show that the long cycle acts by promotion, and then the fixed points of promotion are counted by the trace of the long cycle, and then you throw 100 years of character theory at it. And then you get the Q-hook-length formula and everything works. Anyway, so the main sticking point and the annoying point, right, is that this rectangular condition. So can we get rid of this? And that's sort of the dream is just like, just remove this rectangular condition and maybe we can make things work. Obviously that doesn't work, otherwise Rhodes would have probably proved it. So here's a kind of easy non-rectangular example. We take that partition 3, 2, and I'm ordering my basis in this particular way. So remember, whenever I write a tableau, I really mean the Kazhdan-Lusztig basis element associated to that tableau. So I can calculate using computer program the action of the long cycle. So I get a matrix. It's not a permutation matrix, so our theorem doesn't work in general. But let's just do the naive thing and look at the promotion matrix. So I just take the promotion of all the tableau and write that down. And I'll give you a second to look at it. Maybe you'll notice things are working nicely. The promotion of every tableau appears with non-zero coefficient in the action. So the long cycle does act by promotion up to sign, just as like Brendan Rhodes said, except maybe we get some other terms. And if you like stare at it a little bit longer, you'll notice that the other terms you get are ones that whose promotion has already appeared. So with this ordering of the basis, I'm only getting things that have already kind of appeared to the left. So there's some kind of lower order term thing happening here. And once we realize this, that you could kind of do this and weaken your condition of a permutation matrix to this sort of permutation up to lower order terms, we just thought, well, let's shove it in another permutation and see what happens. So I choose another permutation, I calculate the action, And so notice the first non-zero element of every row has its unique column. And so I can extract a bijection out of this. And so I get some bijection on my standard Young tableau. So what I want to tell you is, first of all, which elements does this work for? Second of all, what is this bijection? So if I give you some element, how do you know, or some permutation, how do you know which bijection this encodes? And then thirdly, like, of course, why does this happen? What's going on? Okay, so I'll jump to the main theorem. So this is what we saw already in the example. The long cycle acts on the Kazhdan-Lussig basis by promotion up to sign with possibly some lower order terms. And this works for, we completely rid ourselves of rectangularity. So this works in any spec module. And in fact, I can tell you exactly what those lower order terms are. So this del operator removes the largest box from both tableau, and then I compare the shapes in dominance order. But actually what this really means is just that the largest box of R occurs in a higher row than it does in T. So I act by the long cycle, it gives me promotion, and then possibly some, like the largest box can move upwards and get a new term. And then sort of the full generality that we could prove this theorem is that you can take any separable permutation, which are this special class of permutations, and the action encodes some bijection on my basis, and then again, some lower order terms. And this bijection is unique, and this order, so they both depend on the permutation themselves. But the very nice thing is that in this case, I can actually tell you exactly what these permutation and this order is in terms of the combinatorics of standard tableau. So it's a completely constructive proof, and we'll see that. Okay, so first of all, just why do I care about separable permutations? So recall my symmetric group, I'm treating this as a Coxeter group. So I'm generating it by these adjacent transpositions that swap I and I+1. I take some subset of those, I can generate a parabolic subgroup, and this has some distinguished longest element. Okay, good. And then the separable permutations are equivalent to the following things. So you can define them in terms of some pattern avoidance. You can define them in terms of these oriented binary trees. But for our cases, what we care about is they're specifically the permutations that can be written as products of longest elements over a decreasing chain. So I take a decreasing chain of subsets, I take their parabolic subgroups, I take their longest elements, and then I take the product. If I do this for all decreasing chains, I get exactly the separable permutations. And so there's a lot of combinatorial structure. Here's the generating function just for fun. There's kind of lots of ways to define these, and they've already come up many times in the literature. But for our purposes, this is why we care about them. Okay, so to justify kind of the general theory, let's look at the long cycle first. So I take this specific parabolic subgroup, which is isomorphic to, it is the subgroup which just swaps around the first n-1 things. So I take the first n-2 generators, so I get the Sn-1 living inside Sn. And then the long cycle has this decomposition. So if I swap the first n-1 elements and then the whole thing, that gives me the long cycle. And okay, so I want to find the action of this Wj. I want to see how this acts, and then I can just combine it and get what I want. So I take this ordering on my basis. So this comes from the ordering I had in my theorem. I first take the tableau with the largest box in the first row, and then the tableau with the largest box in the second row. And so notice when I act by Wj, the red tableau just gives me more red tableau. And then the blue tableau, I get a bijection on the blue tableau, and then maybe I get some red tableau as well. And these are the lower order terms. But really, like, this is acting by this upper block triangular matrix. And in fact, whenever I act by an element of S4, this red block that I can extract gives me a copy of the spec module for 2,2. So really, like, what's happening here is S4 is just acting on the smallest 4 boxes. It's just pretending I was living in S22. And I just act on the smallest 4 boxes and then just add the 5 box back when I need to. And these blue tableaus are the same thing. I kind of ignore the 5 box. I just act on the smallest 4 boxes as if I was in S31 in this case. And then possibly I might get some lower order terms. But like, really, I get this decomposition into my spec modules. So once I have this, I know how the longest element acts in my smaller spec modules. It acts by evacuation. So I can just delete the largest box, evacuate the remaining 4 boxes, and then add the largest box back. And this is exactly the bijection that's being encoded here. So I call this J evacuation for this specific J. So this is the delete, evacuate, undelete. And so it acts by this permutation up to lower order terms. And then to find the action of the long cycle, I just apply the long element. And so the long element acts by evacuation. And so to find the action of the long cycle, I do this J evacuation and then evacuation. And again, everything's happening up to these lower order terms that you see. And then it turns out in this case that this product of evacuations is exactly the promotion map, which is kind of the surprising connection. So really, I'm thinking about the promotion map as a product of these special evacuation maps. Okay, at this point, are there any questions? Because this is kind of the key idea, and then we're going to generalize this to the separable permutations. Yep.
So usually you build evacuation as a sequence of promotions, right?
That's a good question.
You're doing it the other way around?
Yeah, I'm doing it the other way around. So you can define evacuation as, in terms of the promotion map. But for our purposes, we know that the long element acts by evacuation. And so like, really, I want to write everything in terms of evacuation. Because really the evacuation and the long element are kind of my key building blocks. Any other questions? This is all good. So I should note as well that this happens, this kind of upper block triangularity, where you get these lower order terms when you act by S4, this happens over the Young basis too. So this is how you get the classical branching rule. Well, this is one way to see the classical branching rule. So maybe it's not too surprising it also happens over this basis. So what's maybe more surprising now is we're going to do this for general parabolic subgroups. So here are the ingredients I need. I take any parabolic subgroup, and I want to find some ordering on my basis such that anything in that parabolic subgroup acts by an upper block triangular matrix. And moreover, I need my blocks to be irreducible representations. So what I'm really looking for is a Jordan-Hölder filtration of my Kazhdan-Lussig basis, or of the Speck module over this basis, in terms of any arbitrary parabolic subgroup. And very surprising me, this is maybe my favorite part of this kind of work, is that this happens incredibly nicely in terms of the combinatorics. So let's do an example. We look at a tableau on 9 boxes. It's rectangular in this case, but that's just because it made the ticks easier. So I take my parabolic subgroup, which permutes the first 3 elements, and then the next 2, and then the next 4. And how I really want you to think about this, the intuition, is that this subgroup is acting on the first 3 boxes of my tableau, and then it acts on the next 2 boxes, and then it acts on the next 4. So it really like splits up my tableau and then acts on each component separately. This is what I do. I take my tableau and I write it as a list of 3 skew tableaus. So I take the first 3 boxes, then the next 2, and then the next 4. So I get this list of skew tableau. Okay, and now I want to see if I act by an element of my parabolic subgroup, when does another Kazhdan-Lussig basis element appear? So I take my action, I expand it out, and then I look for non-zero coefficients, because then that should appear like higher up in my matrix. So in my ordering. Okay, so when does that appear? And then it turns out we have these 3 very nice combinatorial conditions that tell me exactly when this happens. Or it gives me, it's one implication. So suppose it appears. First condition, if I look at the outside shape of each of my skew tableaus, so I decompose R into R1, R2, R3, and T1, T2, T3, and I look at the outside shape at each point, I get a dominance order comparison of the shapes. Okay, so that gives me some ordering. And if 2 tableaux are equivalent here, then they have the same like decomposition shape. So in this case, the subgroup really is acting by, it acts on the first skew tableau, and then the second, and then the third. Okay, but we have more conditions. If they're all equalities, I can rectify all of these skew tableaus. This is some procedure that gives me standard tableau of some shape. And then I also get a dominance order comparison in these rectifications. And then if this is also true and they're all equivalent here, I also need each of these tableaux to be dual equivalent to each other, which is, again, some other combinatorial condition, which says that like shapes are preserved under sliding. But I get these 3 combinatorial conditions on my skew tableau. And so this gives me an ordering. And the equivalence classes under this ordering are going to be the tableau I can get by replacing any skew part with something else that's dual equivalent to it. So this gives me some sub-representation after I quotient out by the smaller things. And the big theorem is that this sub-representation I get is irreducible. And it's an irreducible representation for Sj. And moreover, so in the case with the long cycle, I just deleted the largest box and then I looked at the shape. And that was my Speck module. So here, Sj is a product of symmetric groups. And so the irreducible representations are products of Speck modules, or tensor products of Speck modules. How do I know which Speck module I'm living in? I do this. I decompose, I rectify all the pieces, and I look at the shapes. So this lives in S21 tensor, S11 tensor, S211. And the isomorphism is like exactly this rectification map. So everything works sort of as nicely as possible. So let's look at an example maybe, because that will help. So I take my tableau of shape 321 and I act by S3 times S3. So again, I'm acting on the smallest 3 boxes and the largest 3 boxes. So here I've drawn the order. The gray kind of dotted boxes are the equivalence classes. And when I act by anything, I get anything to the left or in the same box. Okay, so first thing you notice, so I'll put on the shapes as well. So this is the red shape and then the blue shape after I rectify. So notice that I first order by the red shapes in dominance order, and then within an equivalence, within like a red shape, I order by the blue shapes. And then, so the key point, this key like point of interest are these 2 blocks in the middle. I get 8 tableaux that have shape 2-1, and then the blue also has shape 2-1. And I get 2 separate dual equivalence classes. So what this is telling me is that when I restrict down, I get 2 copies of the spec module S21 tensor S21 inside my decomposition. So this is giving me a Littlewood-Richardson coefficient of 2. And so this kind of proof and this result actually exactly recovers the theorem of Littlewood-Richardson coefficients about they're counted by the number of tableaux of shape lambda minus mu that rectify to some tableau of shape mu or some variation of those partitions. But it's exactly rectifying that, exactly recovering that Littlewood-Richardson rule. But I can do this for like any combination of shapes, and I just split up and rectify everything, and it all works very nicely. Okay, so I thought that was very nice. And then now we can look at the action of the longest element. So as I said before, the irreducibles are tensor products of spec modules, and they have a natural tensor product of the Kazhdan-Lussig basis elements. And so the longest element acts on this by just evacuating each piece. Again, up to sign everywhere, because that's what happens in general. Okay, so I look at my tableau. I forget about everything to the left of it, so I forget about this coset below. And now I want to find the action of the longest element. So what I do is I take this isomorphism down to my irreducible. So now this gives me a tensor product of 3 tableaux. I act by the longest element inside my irreducibles that evacuates each of the skew tableaux. And then I unrectify. So I shift everything back so that it makes the same shape. Everything's dual equivalent. And then because this was an isomorphism, this has to give me exactly the action of the longest element. And so I get this special map called J evacuation. So I just evacuate each of these skew tableaux. And then the longest element acts exactly by this J evacuation map. And then because I added this coset back, I then get lower order terms. And then everything happens up to sign. But then that recovers the main theorem. And then once I have this, I just combine longest elements. And the reason I had to take decreasing permutations was because then these special lower order terms I have kind of imply the next one. So having lower order terms implies that they're also lower order terms for the next piece, etc. So then the bijection I get is just the product of these J evacuation maps as I kind of move out. And so again, like we recover in any arbitrary shape that this longest element and then hence any separable permutation acts by these bijections up to lower order terms. And just a note about kind of an idea of the proof of this, or at least one useful trick I used over and over again, that maybe if you work in this field might be helpful. So this is the generator action, and it relies on these mu values, which depend on tableau, but really they depend on permutations. And the way you go between permutations and tableau is through the RSK correspondence. So you fix some choice of Q, some recording tableau, and it doesn't actually matter which one you choose. It turns out like these all have the same mu coefficient. So it doesn't matter which one you choose, but you have to choose one at some point. And the thing I realized was you should really kind of always choose this one. So you write the elements going down the columns. And if you do this, the inverse image of RSK is really easy to find. So to find the permutation, you just take the column reading word where you move bottom to top and left to right. But you get a very nice description of the inverse of the RSK map. And this lets you convert combinatorial facts about standard tableau into combinatorial facts about permutations and vice versa. So for example, Bruhat order becomes dominance order. And when I take these J decompositions into skew tableau, equality of shapes becomes living in the same coset under SJ. And I can also define these mu coefficients in terms of skew tableau, and this lets me define the skew spec modules. and all these other sorts of things. Okay, thank you very much. Hopefully you found something interesting or you had a nice nap.
Thank you, Fern. Are there any questions?
Thanks for the nice talk. I was wondering, in the case of Brendan Rhodes' results, that shows in particular that promotion has a nice order that we can understand. Are there results that one could hope for in the more general case that you're looking at for like understanding the order of promotion? And do your results let us get towards proving such things?
Yes, that's a big question. So like kind of the ideal hope of this originally was like, well, maybe not, maybe that was too much of a dream, but maybe if you can generalize this one part of the theorem, then everything works and you can find the order of promotion. So far I've thought a lot about this and I haven't really been able to get anywhere. So I can tell you at least the main difficulties where maybe I'm hiding some stuff under the rug. So the nice things about Brendan Rhodes' result in particular is that this sign is constant everywhere. So this sign is the same for every tableau of that shape. Whereas maybe if I go back to my action, so notice like here I'm getting plus and here I'm getting negative. So when I take the trace, I could get some sort of cancellation happening, and that's quite bad for trying to do this trace stuff. And then secondly, like it's possible that one of these lower order terms sort of happens to live on the diagonal, and then I could be counting it even though I kind of don't want to. But there's a natural way to describe this in terms of QR decomposition. So if I take the QR decomposition of this matrix, the Q matrix is the generalized permutation matrix for promotion. So if there's some way to kind of ignore the upper triangular part, which could be possible, like maybe there's some linear algebra trick, I don't know, then it's entirely possible we could get something out of this. But as it stands, it seems like I'm still losing like a little too much information to recover promotion order.
Okay, thanks.
Are there some more questions?
So do you have any hope of finding some type of cyclic sieving phenomena here? Maybe not with promotion, but with some other cyclic group action?
Yes, so that's a very similar question. So one thing you can ask is like, in which cases are these lower order terms trivial? So when these lower order terms are trivial, then you can do this, like essentially what Rhodes did. Unfortunately, the way it seems is that basically, so for the long element, the order is trivial because you just get exactly this evacuation. And then the reason it's trivial here is because when you take the isomorphism down, you just get exactly one spec module. So when you take your branching rule, you just get exactly one irreducible again, because there's one corner to delete. But in general, those are the only two cases where you don't get lower order terms in this type. So in other types, maybe it's different, but yeah, in type A, this is the only one. Yeah.
So I'm wondering, is there a way to get a better grip on the representation theory because you have these operators?
Like in terms of the bijections or the...
I mean, we already understand spec modules pretty well, right?
Yeah.
But if you have these actions on the basis elements, what does it tell you about the representation?
It's a good question. I mean, I think the representation theory, maybe like the branching rules are kind of more important to that. And in fact, sort of in the proof of those branching rules, I'm not entirely sure if it's necessary, but I use this fact about the long element acting by evacuation in order to recover some of those results. And so it seems like those sort of branching rules where you can just split up and do this over any parabolic subgroup seems to be sort of unique to the Kazhdan-Lustig basis. And in particular, you kind of need this long element action. And I've wanted to try and look at the Young basis and see if I can recover the same sort of results. But
the Garcia-Stanton descent basis too.
Right. Yeah, exactly. And see if, yeah, similar things happen, but the Kazhdan-Lustig basis really seems like the right basis to be doing this stuff over.
Okay, thank you very much again.
Thank you.
And now this is a time for coffee break. So we'll start over at 4 o'clock. So I guess everybody are here now. So the next talk will be given on quantum Young-Baxter moves by Takafumi Kono.
Thank you. Thank you for introduction and thank you for giving me such a great opportunity. Today, I will talk about quantum Yang-Baxter moves, which are important maps in the theory of quantum outcome model. Now, let's start. First of all, I will talk about the purpose of this work in this introduction. Now, our main object is the quantum outcome model, which is introduced by Renard and Rybovsky. The quantum outcome model appears in many branches of mathematics. For example, Schubert calculus and the representation theory of quantum affine algebras. Now, we take a column-shaped key-leaf crystal, which is a combinatorial model for a certain finite dimensional representation over a quantum affine algebra. If the root system is of type A, this column-shaped key-leaf crystal is realized by using the tableau of column shape. So this V of P1 is a crystal of tableau of column shape. We consider the tensor product of key-leaf crystals. Then the following fact is known by Renard, Naito, Sagaki, Schilling, and Shimozono. We consider tensor product, then this tensor product can be realized by using the object of the quantum outcome model. This is called an admissible subset. I will explain later. So this tensor product of key-leaf crystals are realized by using the theory of quantum outcome model. Here, in this A of gamma, this gamma is a suitable sequence of roots, which is called lambda chain. So this is a sequence of roots associated to lambda. Now, we focus on the tensor product of key-leaf crystals. We consider to change the order of tensor product. Then we obtain these two crystals. And the well-known fact is that these two crystals are isomorphism. This isomorphism is called a quantum combinatorial R matrix. If the root system is of type A, this crystal is realized as the crystal of tableau. Then this combinatorial R matrix is realized as Ju Takan. Next, we focus on the theory of quantum outcome model. As I mentioned before, this A of gamma is a main object of the quantum outcome model, and this depends on the choice of dominant integral weight lambda. Moreover, depends on the choice of lambda chain. This is the sequence of roots associated to lambda. Therefore, the structure of A of gamma depends on the choice of lambda chain. However, the following theorem is known. This is proved by Renard and Rybovsky. These two crystals for different reduced lambda chains, reduced means the shortest, then these crystals are isomorphic. And this isomorphism is realized combinatorially by using a sequence of quantum Yang-Back star moves. Therefore, we can conclude that the structure of A of gamma does not depend on the choice of gamma, reduced lambda chain. To summarize the situation, we obtain the following commutative diagram. First, there exists an isomorphism, a bijection between the object of the quantum Markov model and the tensor product of key-free sticking crystals. Then we have a combinatorial R matrix. If root system is of type A, this is realized as the Ju-Takan. Moreover, there exists a sequence of quantum Yang-Back star moves. Then this diagram is commutative. So we can conclude that the quantum Yang-Back star move can provide a realization of combinatorial R matrix for uniformly or untwisted affine root systems. Note that Ju-Takan is for type A, but this quantum Yang-Back star move is not necessarily for type A. So this is a root system generalization of Ju-Takan. This is the background. Now, we have a generalization of admissible subsets for arbitrary Weyl group element and arbitrary integral weight. In the previous slide, we use A of gamma, and this A of gamma is for dominant integral weight, and W is fixed to the identity element of the Weyl group. So we have this generalization, and we have the following applications of A of W gamma. First, the Schubert multiplication formula in the K group of semi-infinite Frank manifolds. Schubert multiplication formula is an expansion formula of the product of Rhine bundle class and Schubert class, in this case, semi-infinite Schubert class, into the infinite linear sum of Schubert classes. In this sum, this A of W gamma appears. Also, we can apply this A of W gamma to the quantum K group of Frank manifolds. Moreover, we have representation theoretic application. So we can obtain character identities of level 0 dimensional modules for quantum affine algebras. Now, we have a question. So we have a generalization of admissible subsets for arbitrary W and arbitrary gamma. So the question is that, can we generalize the quantum Yang-Back star move to the arbitrary admissible subset? If this question is true, we can conclude that the structure of A of W gamma is independent of the choice of lambda chain. However, it is not so easy. In general, these two sets have different cardinalities. Therefore, we cannot construct a bijection between these two sets. As a result, to generalize quantum Yang-Back star move, we need a new approach, normal bijection. To solve this problem, our main idea is a bijection, which is signed bijection introduced by Fisher and Konvalinka. A bijection is defined as follows. First, we take signed set S and T and explicit subset of S and T, denoted by S0 and T0. Then we construct sign-preserving bijection between these two subsets. Also, on the outside of these subsets, we construct a sign-reversing involution, iota. Then we obtain three maps, iota S, iota T, and phi. This triple is called a bijection. So this is normal bijection. So our main result is the following. By using this idea of bijection, we can construct a bijection between these two admissible subsets, which is structure preserving. So we want to call this a generalization of the quantum Yang-Baxter move. This is normal bijection. In this talk, I will explain this main result. Now, this is a notation of this talk. First, we take a simple real algebra and its root system and its positive roots and its weight lattice and the set of dominant integral weights and the correct lattice usually. Also, we take the while group of G and length function on W. This is the plan of this talk. First, I will introduce the notion of the quantum outcome model. And then I will explain the main result about quantum Yang-Baxter moves. Now, I will introduce the quantum outcome model. To do so, we need the notion of the quantum Fourier graph defined by Brent, Fomin, and Postnikov. The quantum Fourier graph is a directed graph on the while group whose edges are defined as follows by using length function. Note that the Fourier edge is just a covering of the Fourier order. Here's an example of the quantum Fourier graph in type A2. Next, we need the notion of lambda chain. I will omit the precise definition of lambda chain, but I will explain the example. The lambda chain is a sequence of roots associated to integral weight lambda. First, we take the fundamental alcove here. The definition is this. And then we translate this fundamental alcove by minus lambda. Then we obtain a new alcove. Then we take a directed path from fundamental alcove to translated alcove. Finally, we record the negative of the direction vector. In this example is type A2, and this direction is minus alpha 2. Alpha 2 is a simple root. So we record minus alpha 2, so alpha 2. The negative of minus alpha 2 is alpha 2. Then the next direction is minus alpha 1 minus alpha 2. So we record alpha 1 plus alpha 2. Like this, we obtain the following sequence. This sequence is pi 1 plus 2 pi 2 chain. Here, this pi 1 and pi 2 is a fundamental weight. Then we call this lambda chain reduced if this path is shortest. In this case, this sequence is shortest, so this is reduced pi 1 plus pi 2 chain. So next, I will introduce admissible subsets, which are main objects of the theory of quantum outcome models. So first, we take arbitrary while group element and integral weight and lambda chain. Then the subset A of index set is called a double admissible subset if this path is a directed path in quantum Fourier graph. In this case, we denote by end of A the end point, the terminal of this path. Also, we pick up all quantum edges from this path and sum up all levels by taking correct and absolute value. This is called down of A. Moreover, we count the number of negative roots corresponding to these indices belongs to A. Then this number is denoted by N of A. Now we note that there exist more two statistics. But these statistics are so complicated, so I omit the precise definition. So there are important four statistics: end, down, weight, and height. Also, we can define the sign function by using this n of a. Then we define a of w gamma by the set of all W admissible subsets. So by using this sign function, we can consider this a of W gamma is a signed function, signed set. I'm sorry, signed set. So this is the introduction of the quantum Arco model. Now, I will explain the main result about quantum Yang-Baxter moves. To do so, we need the notion of Yang-Baxter transformation. The Yang-Baxter transformation is a deformation procedure of lambda chain. How to deform? First, we take a segment of the form alpha, S alpha beta, S alpha S beta alpha, da 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 beta. Then we reverse this segment. Then we obtain a new sequence of roots. In fact, this sequence is also a lambda chain. So this is the deformation procedure of lambda chain, and this is called a Yang-Baxter transformation. In addition, we need the deletion. This is also a deformation procedure of lambda chains. First, take a segment of the form beta minus beta. Then delete this segment. Then we obtain a new sequence. So this is also a lambda chain. So this deformation procedure is called a deletion. Then there is an important fact. So this fact explains that the deformation procedures of lambda chains is so only need Yang-Baxter transformation and deletion. So this fact says that first we take any lambda chain, and then we take any reduced lambda chain. Then we can deform the first lambda chain to the second lambda chain by using only Yang-Baxter transformation and deletion. So these two deformation procedures are elementary. Now, I will explain the quantum Yang-Baxter move for dominant integral weight. First, we take dominant integral weight and take two reduced lambda chains, gamma 1, gamma 2. Such that gamma 2 is obtained from gamma 1 by using a Yang-Baxter transformation. In this case, we can construct a bijection between these two admissible subsets. Note that this while group element is fixed to the identity element in this case. Also, this bijection is structure preserving. So therefore, there exists a structure preserving bijection between these two sets. Therefore, we can conclude that the structure of A of E gamma does not depend on the choice of lambda chain, reduced lambda chains. This is the result of Renaud and Lubovsky. And this map is called the quantum Yang-Baxter move. In fact, this quantum Yang-Baxter move is compatible to the crystal structure. In fact, this A of E gamma has the crystal structure, and this map is a crystal isomorphism. Also, as I mentioned before, this quantum Yang-Baxter move is a root system generalization of Ju Takan. Now, I will explain our main result of the generalized quantum Yang-Baxter move. So as I mentioned before, So to generalize quantum Yang-Baku star move, we need a new approach, normal bijection. And the idea is the surjection. Now I will explain our main result. First, take an arbitrary integral wave lambda and arbitrary while group element. Then we take two lambda chains, not necessarily reduced, such that the gamma 2 is obtained from gamma 1 by using Yang-Baku star transformation or specific deletion, such that a segment of the form beta minus beta is deleted, but we assume that beta is not a simple root. It is important. In this case, we found explicit subsets of AW gamma 1 and A of W gamma 2, such that first, we can construct a sign-preserving bijection between these two subsets. Also, this bijection is structure-preserving. How about the outside of these subsets? We have other result. On the outside of these subsets, there exists involution, which is sign reversing. Also, this involution is structure preserving. So this is our main result. And to summarize, we can explain this result by using this picture. First, we take subsets A0 of both sides, and then we take a bijection. This is sign preserving and structure preserving. How about the outside of the subsets? We can construct an involution. This is sign reversing and structure preserving. Then we obtain these three maps. First, sign reversing involutions and sign preserving bijection. So we can think that this is the surjection. And we can call that this surjection is a generalized quantum Yang-Baku star move. And this is normal bijection. So this is our main result. Next, as an application, we can prove the preservation of generating functions, which is important in the for application to the K theory and quantum K theory. First, we take an affine while group. And then we take an element of a affine while group. Also, we take lambda chain. Then, generating function over the set of admissible subsets is defined as follows. First, we take these four statistics, and then take the sign function. Finally, sum up these terms over all admissible subsets. So we call this a generating function. So our second result is the following. First, we take an integral weight lambda and arbitrary affine while group element. Also, we take two lambda chains such that gamma 2 is obtained from gamma 1 by single application of Yang-Baku star transformation or specific deletion, such that the segment of the form beta minus beta is deleted. However, we assume that beta is not a simple root. In this case, we can prove the preservation of generating function. This is important because this can be applied to the proof of Shibare multiplication formula in the K group of semi-infinite Fpsac manifolds or quantum K group of Fpsac manifolds. How do we prove the Shibare multiplication formula? First, we take a well, we take a Chevalier formula for dominant and anti-dominant weight. Then we combine these two formula. Then deform these. So in this deformation procedure, we use these two procedures. And due to this preservation, we can prove the Chevalier formula. This is a proof. And I'll explain that this generating function is related to the Chevalier formula because this sum is closely related to the right-hand side of Chevalier multiplication formula, closely, very similar. So we can prove the Chevalier formula by using this generating function. This is the second result. And now, this is the conclusion of today's talk. First, we obtain the generalization of quantum Yang-Baxter move as a surjection. It is no more bijection, but surjection. Then, by using this surjection, we obtain the preservation of generating functions. Finally, by using the preservation of generating functions, we obtain the combinatorial proof of the Chevalier multiplication formula for in the equivariant K group. Oh, I forgot the equivariant. I'm sorry, this is T. Equivariant K group of the semi-infinite Fpsac manifold. This is first proved by Renat Naito-Sagaki, but we can give a combinatorial, purely combinatorial proof for this formula by using this theory. This is the end of my talk. Thank you very much for listening. Thank you.
Thank you very much, Takafumi. Just the perfect timing. Any questions?
So you said that you pick a subset of AW gamma and then perform the surjection on that. So
Yeah.
what is that A naught W gamma and how do you exactly choose it?
Yeah, sorry.
So you
Yeah.
choose a subset A naught W gamma, right?
Yeah.
So what are the properties that the subset has? Like how do you specifically choose it, or is your proof just like that subset exists?
No, so I cannot understand the question, but so your question is the yeah.
The subsets.
Ah, I see. So I forgot to prepare the explanation slide, but we can so we can choose this subset by observing this set explicitly and see these statistics, and we can do the matching of these two. So there are two elements such that the sign is equal and these four statistics are equal. And one more case. There are two elements in this set and sign is different and these four statistics are equal. Then we can pick up if there are two elements in this set, this whole set, and this whole set, we can do matching these two elements. So do matching. So elements matched belongs to this set, and elements such that there are two elements and sign is negative, sign is different, and these four elements are equal, then we include these two elements in this outside subset. This is the way to choose the subset.
Thanks. That was a really nice talk. I wanted to ask about the surjections.
Yes.
So were they invented for this theory, or are there other places where these come up? Are there other uses for these?
I don't know the application of the surjection, but
Seems like someone does.
Yeah, this notion of surjection was invented by Fischer and Konradinka.
Yeah.
But the setup that they have is the setup of the Garcia-Milne involution principle, which was invented to construct a bijective proof of the Rogers-Ramanujan identities.
Yeah.
And Fischer and Konradinka, they wanted to set up a bijection between a certain class of alternating sign matrices and another class of plane partitions.
Yeah. Thank you.
So I would like to add to this that this actually comes up in a completely different context, in the context of the Wald-Brouwer algebra. Sorry, Wald-Brouwer algebra. I have difficulties pronouncing R's, where the multiplication is exactly what you would expect or would hope for. I think due to Benkert.
Well, maybe can you really quickly say what elements specifically are in the A0 subset?
Yeah. So this subset?
Yes. Yes. What characterizes it? What, I have all of my AW. How do I know if it's an A naught?
But there are no characterization now. So we have to find the how to characterize these subsets. So these subsets defined by using gamma 1, gamma 2, and W. But there are no explicit description.
So your proof is not constructive.
Yeah.
Okay, I see. Thank you.
Is there some more questions?
So in type A, is there an easier way to phrase this, or is there some known result already that, I mean, you can elaborate maybe? So in type A, is there an easier way to phrase this in a more concrete manner?
I think it's not so concrete, but I don't have any idea. I'm sorry. So this map is not so explicit, but using we can construct this map by using R matrix and so forth. So this is not so explicit.
Okay.
Yeah.
I guess we will send the Kafumi again.
Thank you very much.
Oh. So our next speaker is Oustin Bendali from the Université de Lorraine, who will speak us about the merchant Jack conjecture.
Sorry? Okay, thank you. I would also like to thank the organizers for this invitation. So my talk today is about this long-standing conjecture of Gundel and Jackson called the matching Jack conjecture. So today I give half an answer to this question by proving the integrality property using some surprising connection with the Farah-Ayman algebra. As you can guess, there is a remaining part of this conjecture to prove some positivity property yet to be proved. So I would like to start by some motivations about behind this conjecture, more precisely with this result of representation theory, which puts together sure functions and connection structure coefficients in the permutation in the symmetric group. So what we have on the left side of this equation is the sum over all integer partitions theta, and then up to some normalization factors, we have a product of the same sure function as theta, but expressed in 3 different power sum bases, which we denote P, Q, and R. And then what we do is that we expand this function in the power sum bases associated to these 3 different alphabets, P, Q, and R, and the coefficients which appear depends on, so always there's some normalization here related to the number of permutations of cyclic type lambda, and the coefficients which appear are indexed by 3 partitions, lambda, mu, and nu, which have the same size. And what we obtain is that these coefficients actually they count the number of ways to decompose a fixed permutation sigma lambda of type lambda into 2 permutations sigma 1 and sigma 2, which has respectively cyclic type mu and mu. Okay, so this is just a generating function version of 2 classical results of the representation theory of the symmetric group. So the first result tells us that sure functions, when we expand them in the power sum basis, basically we have the characters of the symmetric group which appear. And the second result gives us that tells that the structure coefficients in the symmetric group can be expressed as a sum of 3 as a sum of the product of 3 characters. So one other reason people are interested in such generating series is that it's also related to counting maps. So these coefficients actually they count maps on orientable surfaces. Just some graph drawn on an orientable surface. For example, here we have an example on the torus, and this is actually a consequence of the fact that these maps can be encoded by pairs of permutations. So the first thing that Goulden and Jackson proved is that we can do the same thing for another family of symmetric functions, which are the zonal polynomials, which I'm not going to define at least in this slide. And so it's always the same thing. We take the product of 3 zonal polynomials in 3 different alphabets of power sum functions. The normalization is a little bit different. And then when we expand this in the power sum basis, the coefficients which appear here has always a nice combinatorial interpretation, but this time we have matchings instead of permutations. So basically matching, we can think of them as a generalization of permutations, and more precisely, we have a bijection between permutation and some particular type of matchings, which are called bipartite matchings. And the idea of the proof is quite similar, except that here, instead of having a representation theory of the symmetric group, we have a Gelfand pair of the symmetric group and the pair octahedral group. And as always, we have a nice connection with maps. So this is also, this generating series also count maps, but now on general surfaces. And what I mean by general surfaces, these are maps orientable or not orientable. So a natural question arises here is that, is there a way to unify these 2 equations which look very similar? And at least on the algebraic side, this left side, these red objects, we have a natural candidate, which are given by Jack polynomials. So Jack polynomials are symmetric functions, always indexed by integer partitions, but which also depend on this one deformation parameter B. So actually, this is the definition of Jack polynomials given by MacDonald. It tells us that they are basically characterized by two properties, some triangularity property in the monomial basis and some orthogonality property with respect to some B deformation of the classical whole scalar product on the symmetric group. So this abstract definition is not very important for this talk. What's really important is that if we take B equals 0, basically Jack polynomials are sure functions, and if we take B equals 1, we recover zonal polynomials. So the idea of Gould and Jackson is that, okay, we replace in this generating series sure functions or zonal polynomials by Jack polynomials, and then we expand them in the power sum basis. So we have some coefficients here which appear always indexed by 3 partitions of the same size, but which also depend on this deformation parameter B. And the question, do these coefficients have some combinatorial interpretation? So at least we know that for B equals 0 and B equals 1, this is the case. So this summarizes a little bit the two first slides. So for B equals 0, this counts pairs of permutation or equivalently bipartite matchings. And for B equals 1, this counts matchings bipartite or not. So what Gould and Jackson conjecture in this matching Jack conjecture is that these coefficients, actually these C coefficients, actually they are a polynomial in the parameter, in the deformation parameter B. And these polynomials have non-negative integer coefficients. Okay, and it's not very difficult to see that given the results for B equals 0 and B equals 1, this algebraic formulation has a combinatorial reformulation, which says that actually this coefficient C can be written as sums over matchings. So what does it say is that we can define there exists some statistics on matchings which have non-negative integer values. And actually these statistics are supposed to quantify somehow the non-bipartity of the matching. So in particular, we ask that the statistic is 0 if and only if the matching is bipartite. And then this statistic also satisfies that we can write the coefficient C as sum over matchings of some types, and in which we assign to each matching this B weight of the form B to the power of the statistic of the matching. Okay, and actually what makes this conjecture hard and interesting is that we have, sorry? Yeah. Excuse me, I don't continue.
Could you clarify what a bipartite matching means? Because I think it would always be, what I understand of a matching, it would always be bipartite.
Okay, so I didn't precise the definition, but basically we consider matching so these are perfect matchings, and we consider matching on the sets of even size, and so there are these integers and integers with hats, and a bipartite matching would be a matching relating always an integer without hats with an integer with a hat. So that's sorry, a hat. Sorry, excuse me. At the type.
And I also don't understand what the type.
Okay, I didn't define it because it's a little bit technical. We should fix two matchings, and we can think of it just as a generalization of permutation. But I can give more details about this later. So as I said, okay, we have no B deformation of this representation theory that allow to prove the results for B equals 0 and B equals 1. So we have to come up with some new techniques to deal with this conjecture. So a priori, what do we know about these coefficients? So just from the definition of Jack polynomials and some basic properties about power sum functions, we know that these coefficients actually are rational functions in B. So we are very far from the conjecture of Gould and Jackson. And almost 20 years after this conjecture has been formulated, Doenga and Ferré proved that these coefficients actually are polynomials in the parameter B. And they obtained some upper bound on the degree of these polynomials. So I write it here with the in terms of ranks of these permutation of these partitions. And what I call a rank is just the size of partition minus its length. And so what we should do now is to study the coefficients of these polynomials in order to obtain the matching Jack conjecture. And the result I present today is an integrality result. So we prove that actually the coefficients of these polynomials are integers. And so there is what is remaining to prove is that these coefficients are positive also to have the proof, the full conjecture of Goulden and Jackson. And actually, since the approach here is independent from the approach of Doinga and Ferré, we obtain a new proof of the polynomiality of the coefficients. Okay, so the starting point of the proof is what I call the matching Jack conjecture for marginal sums. And what I call marginal sums are coefficients indexed by two partitions of the same size, lambda and mu, and some integer m less or equal than n, and which are obtained by taking all this sum over all partitions mu over which has length m of this coefficient c with three partitions lambda, mu, and mu. Okay, and if we do this, so this results from a previous work, we prove that actually these marginal coefficients have this nice combinatorial interpretation predicted by Goulden and Jackson. And in particular, we know that these marginal coefficients are polynomial in B with no negative integer values. So just a comment on this result. So this is based on the work of Chapuis and Doinga on the B conjecture, which is another conjecture of Goulden and Jackson very related to the matching Jack conjecture. And the idea of their proof, they came up with the new differential operators, and they use some techniques in the equations, Tut-like equations on maps. And what we do, what we know about these techniques is that we cannot control more than two partitions and one integer. So combinatorially, we cannot, at least with these techniques, we cannot do better. So the idea of the of what I present today is to use some algebraic framework of this Farad-Ayman algebra to transfer at least partially this result to the coefficient C with three partitions. And what I mean by partially is that we transfer the integrality, but we lose the positivity. So the scheme of proof is the following. So we have integrality for the marginal coefficients, and we want to obtain the integrality for coefficients with three partitions. So the first ingredient is this associativity property that I will define in the next slide, which gives us a system of linear equations which relates the coefficient C with three partitions and this coefficient C bar, the marginal coefficients. And the second ingredient is the Farad-Ayman algebra, which says to us that this system is actually invertible in Z. So we obtain integrality information for the coefficient C. So you can already see here why we lose the positivity, because we have some system to invert and we cannot obtain the positivity information. And just one comment on this, so on this approach, this is quite surprising because what we are seeing here is that we have this associativity property which allows to cover the coefficient C with three partitions from the marginal coefficients. And even the fact that this system is somehow invertible, even in Q, we don't understand it combinatorially. And this have some nice applications. For instance, we can obtain a direct a new proof of the matching Jack conjecture for B equals 0, B equals 1, which actually does not use representation theory. Okay, so now I will start by explaining what this associativity property is. So this is actually a consequence of the orthogonality of Jack polynomials, and which is given by this abstract relation for fixed four partitions of the same size. So I will try to give some combinatorial interpretation of this associativity for at least the case B equals 0, because when we take B equals 0, we know that these coefficients have a combinatorial interpretation in terms of permutations. And what we can see is that both of the sides of this equation, they count the number of ways we can decompose a fixed permutation sigma lambda of cyclic type lambda into three permutations, sigma 1, sigma 2, sigma 3 of respective type mu and rho. So we have two ways to decompose, to have such a decomposition. Either we start by choosing the permutation sigma 1 of type lambda. So this will fix the product sigma 2, sigma 3 of some type kappa, and then we decompose this product. Or we can do the opposite. So we start by fixing sigma 3, and then we do we do the opposite, and we obtain the right hand side. Okay. So the associativity property for B equals 0 is just the associativity in the permutation group, in the symmetric group. So now what we are interested in is to have some relation connecting the coefficient C with three partitions and the marginal coefficients. So what we do is that we keep three partitions lambda, mu, and nu, and then we take the sum over all partitions row of length m, and we obtain this relation. Okay, so this is the marginal version of this associativity property. So how do we proceed? Is we try to prove that this coefficient C, lambda, mu, kappa are actually polynomials with integer coefficients by proceeding by induction over the rank of kappa. So how do we think of this equation? Is that we fix lambda and mu, and then we think of nu and m as a couple of parameters indexing this family of equations. So the idea is to select, let's say, a good set of parameters nu m, which allows to select the partitions kappa of rank lesser or equal and r, and to have some information about the partitions kappa of rank r. So, and to do this, actually, we use this upper bound on the coefficient C that I presented earlier. So we have this, let's say, this set of well-chosen parameters nu m that I denote with T, and whose the definition is not very important. But what we know is that for this couple of parameters, we know that when we take the sum over all partitions kappa of rank R, and then we take the product of this coefficient C with three parameters and the marginal coefficients, this sum is a polynomial in B with integer coefficients. And which is what is important here is that the coefficients, the marginal coefficients which appear here, are actually a very particular type of marginal coefficients, which are called top connection coefficients, and are actually independent from the parameter B. And how do we think of this? So we think of it as a linear system in which the coefficients C with three partitions are the unknowns, and the coefficients encoding the system are the marginal coefficients. Okay, so what we want is to prove that the system is actually invertible in Z. So what we say is that, okay, we have the marginal coefficients here are independent from B. So the easiest thing to do is to think of them as their evaluation at B equals 0, because we know that for B equals 0 we have some nice combinatorial interpretation in the symmetric group. So that's what you do, and there is an elegant way to study the coefficient, the structural coefficient symmetric group, which is given by the Farad-Ayman algebra. So unfortunately, I don't really have the time to give this, the technical definition of this algebra. So I'll try to explain the main details of the proof in the context of the symmetric group. So I start by some classical definition. So if you fix a partition n of size, a partition nu of size n, so denoted by C nu, the sum of all the permutations of type nu in the center of the algebra of the symmetric group. So this family of elements actually form a basis of this algebra. And what I recall from the first slide of this talk is that the structural coefficients of these elements are actually the coefficient C evaluated at B equals 0. And we know from this upper bound on the degree of this coefficient that we can restrict this sum over partitions kappa, whose rank are less or is bounded by the sum of the ranks of nu and rho. But here we are just interested in the case where we have equality here. So what we do is that we pass to the graded algebra, which is spanned by the same elements, C nu, but in which the multiplication is a little bit different. So it's just that we take the same sum, but we replace the inequality here by inequality. Okay. And so this is a graded algebra because all elements are have degree given by the rank of the partition indexing the element C nu. Okay, so and we note this this homogeneous component of degree R by ZNR, and this is spanned by this C nu for nu of rank R. So to sum up a little bit about so the connection of these marginal coefficients with this algebra, so this can be seen as the coefficients of this family of elements, which is obtained as a product of some C nu with the marginal sum in the classical basis of the algebra of the symmetric group. And actually, what we prove is that this family is this spanning family for the algebra. And if we do this, we obtain that the coefficients here we are interested in and which encode our system are invertible in Z. So this is the idea of the proof. And what we really prove is that we can extract from this family of, we can choose a subset of T, such that actually this is a basis up to some details of, okay. Just comment on this. So on this family of, on this new basis of the algebra. So these have two parts. The first part is the classical basis, and the second part is part given by the marginal sums. And actually, it's this is a result of Farad-Ayman that these sums they form an algebraic basis of the algebra. So we are kind of have we have an intermediate basis from the classical basis and the basis of Farad and Ayman. And just to comment on the proof. So first we have the stability property of Farad and Ayman, which have proven that proved that this coefficient C indexed by partitions of size n, they can be seen as structural coefficients also in the symmetric group of larger size, just by adding parts equal to 1 to the partitions indexing this coefficient. And actually, this allows to pass to the projective limit over n here. And this is actually the graded Farad-Ayman algebra. And it turns out that it's convenient to work in this algebra rather than the algebra of the symmetric group itself. And the second important ingredient of the proof that we use, two other bases of the algebra. The first one is the one I explained, given by Farad and Ayman, and the second basis given by Matsumoto and Novak, and which is basically the evaluation of the monomial function into the UC-Smith elements. And this diagram just illustrates the transition between the different bases which appear in the proof. Thank you for your attention.
Thank you, Hussein. Other questions?
Sorry, a very elementary question. I thought when B equals 0, there's a symmetry between lambda, mu, and nu, right?
Almost. Actually, there is a symmetry between mu and nu, but not lambda.
Not lambda? But
because actually, we, okay, I'll go back.
No, I know. They're not different.
Okay,
but
so because
identity, I thought
because we fixed the permutation sigma lambda actually here. So there is
but if I look at the
because there is a z lambda here, which breaks the symmetry, but it's just a trick of normalization.
Thank
you.
Some more questions?
So do you get a combinatorial interpretation for the coefficients of the C lambda nu mu of B's?
Excuse me.
So you prove the integrality and polynomiality, right? So you prove, so if you have a non-negative integer coefficient, did you come up with some interpretation for them too?
So
it just comes from the linear algebra.
So yes, so the inconvenient, the disadvantage of such an approach is that we don't really have a combinatorial interpretation, but I think that this kind of approach, it gives some idea for the to have the combinatorial interpretation for the coefficients, actually, because if you imagine that we have a candidate statistic on matchings, and we think of it, we think it's a good candidate for the matching Jack conjecture, what we might prove is that it's an answer for the marginal coefficients. And if we succeed to prove that it also satisfies this associativity property, this marginal associativity property, so it's also an answer for the matching Jack conjecture. But the problem is this associativity on the statistic on matchings, it's very hard because the matching that we use are built on maps, and the associativity is not very natural on them. So
So in fact, you don't believe that this method is likely to help in the other part of the conjecture, yes?
Sorry?
Understood? Because there are two parts of the match-inject conjecture. The first one is polynomiality that you proved, and this is very strong result that was expected for a long time. And there is also other part that is coefficients in terms of interpretation of the graphs. So you think that your method, it will be complicated to use for that part? Well, to prove the whole match-inject conjecture.
Excuse me, can you repeat the, excuse me.
Sorry. Because for the whole match-inject conjecture, you have your part that is you prove that the coefficients are in fact polynomials with integer coefficients. And the second part is interpretations of the coefficients in terms of graphs, yes? So did you make any progress with your approach on the second part?
So for the second part, we have this progression about the marginal coefficients.
Okay.
So yeah, this is so for now. This is I think the best we can do, and this is actually a consequence of the work of Chapuis and Doinga about the B conjecture, and I think that in this direction of combinatorial interpretation, for now this is the best we can do. Yeah, this is a new statistic. Yeah. Exactly. And yeah, this is hard. I think. Yeah.
Okay. So thank you very much again. So the concluding talk of this day is a talk by, we're very lucky to have Professor P.P. Devakanan, who will speak about the history of combinatorics in India. And his talk will be preceded by a very short introduction of his colleague, younger colleague, Amri.
Thank you, Katerina. I just wanted to say a couple of words about Professor Divakaran. Professor Divakaran is a mathematical physicist, and he worked at the Tata Institute of Fundamental Research in Mumbai. For the last 20 years, he has been part of a small but dedicated group, relooking at a lot of ancient Indian texts in mathematics. And he has contributed in a big way to a better understanding of what is known as the Nila School of Mathematics from Kerala. He's also written an authoritative account of the history of Indian mathematics. It's a book published a couple of years ago called The Mathematics of India. And so I'll just hand it over to him now.
Forward, backward, this is the pointer. Right. Thank you for having me, first of all. I have to apologize for the fact that what the discussions in this apparently very stimulating conference are far above my head, so I have not been inside this hall very much. And thanks for turning up for my talk, which is going to be light relief after all the difficult stuff that you've been listening to. Now, the first question I would have liked to ask in a not so formal meeting is, how many people here have heard the name of Pingala? I would imagine not so many. I know, yeah, I've met two of them, and now I know that there are about a dozen. So I'm going to spend a little time explaining not so much who he was, because we don't know very much about him. I'm going to talk about the background in which he came to his interest, and he did what you people are here to celebrate, what it has become since then. Pingala himself lived approximately in the 2nd, 3rd century BCE, that is before the Common Era. And now it is more than 2,000 years, and the subject is flourishing. Witness this conference. Witness the Fields Medals this year. So it's wonderful. I'm very, very particularly pleased that I'm here. Good. So everybody can see what's on it, no? Now, what I'm going to do now is, before I describe his own work, his own contribution to the founding of the subject of combinatorics, I'm going to give a little background about the history of mathematics before him in India. So you know in what setting he came to prominence. Now, there it is. Yeah. So things are clear. Now, the thing to remember is that in India, mathematics of some sort or the other has a very, very long history. It goes back to about 2600 BCE in what is called the mature phase of the Harappan or the Indus Valley civilization, which came to existence in the valley of the Indus River. I'll show you a map in a minute. The Indus Valley people left no records that we can read now. They had a language, presumably a very rudimentary language. We can't read it. Nobody can read it. So we have no account of what they did, except the artifacts that they left behind in enormous numbers, plus plus the seals and sealings on which their script is presented. And they have very interesting qualities. And the first thing is, what about their mathematical knowledge? They knew fairly large numbers because they had weights which went up to a few thousand of the fundamental weighing unit. If you take the smallest as a unit, the highest weight they had was about 3,200. So we know that they knew what to do to go from 1 up to 3,200, mostly multiplicatively, multiplication. So the second point says that in their artifacts, the binary ratio is very, very prominent. They had a very high level of technology. They produced very beautiful, very symmetrical bricks baked in a proper kiln. It's not just roughly made bricks dried in the sun. They were actually fired in very, scientists now tell us, in very highly well-controlled temperatures, the necessary temperatures. So they had high technology. These bricks are always in the edges of the bricks are in the proportion 1 to 2 to 4. So that is the first thing. Then their weights, which are extremely beautiful objects made from semi-precious stones, they also progress in steps of 2, 1, 2, 4, 8, 16, 32, then 1600, 3200, then 64, I forgot 64. So they progress both in a binary ratio as well as in a decimal ratio. So it's very difficult to know how they counted. If they had a base, what the base was, the choice is presumably between 8 and 10. And there are indications which say that 8 is more likely to be the base they used. That's one of the things they did. This depends on certain hypotheses, knowledge of languages and so on and so forth, so I'm not going to get into it. I'm quite convinced that 8 was the base. Then, these weights are doubled, I said, they are cubes. They are in the shape of cubes cut out of very fine stone. So they knew how to take an approximate cube root of 2, because that's how the weights progressed. Now, of course, everybody here probably knows, or most people will know, about the Delians going up to the Oracle of Delphi and asking, what do we do to get out of the situation of the plague that we are in? He said, make an altar which is exactly twice the volume of the altar that I'm already have. And of course, they did or they did not, I don't know. So actually the best part of the industry is the number system as well as the geometry. Geometry is very interesting because, we are talking about before 2000 BCE. There is no evidence that they had the Pythagoras theorem. They had an understanding of it. There is nothing in the numerology of the artifacts which tells you that the Pythagorean triples were known, unlike in Mesopotamia, which came later. So I said these things, Mesopotamia, the old Babylonia, for example, the earliest artifacts, mathematical artifacts, are about 2000 to 800 BCE. And till then, that was the time when the Indus Valley civilization went into decline. But till then, they had extremely close contacts. We know plenty of things have been found. Our things have been found there, and their things have been found here. So it's a difficult problem to settle, but I'm sure it will be settled one day because there's a tremendous amount of work going on in this area. And they made very beautiful intersecting circles. They knew orthogonality coming from intersecting circles. They knew the theory very well, that the common chord intersects the said line of centers perpendicularly. And they used that to create extremely beautiful decorative patterns. And I don't know, Bangalore, the highway to the airport, there used to be lots of avenue trees planted on the left, especially in Yelahanka and beyond. And they had protective little grills made in concrete. And one of them used exact replica of one of the Indus Valley patterns. Yeah, and Indian fabric manufacturer, there's cottage industries people, they use decorative patterns which come all the way from 4,000 years ago. So it's a very, very, very strongly living tradition. So that is the first. Now, we don't know so much about them because now if you insist that I must have a text by which to substantiate what I say, then we have to start from about 1200 BCE. That is when a text called the Rigveda was written. Now, lots of people here, the Indian people who know about the Rigveda, will be very surprised that it figures in a talk on the history of mathematics. The reason for that is that the Rigveda is a religious text. It's a spiritual text. It's a text full of very visionary poetry. It's a very beautiful stuff. But what is mathematics doing in it? The fact is that the Rigveda has the names of about 2,000 numbers in it. A fact which is apparently went unnoticed for a very long time. And of these 2,000 numbers, many are complicated names, not like 1, 2, up to 9, but things like 99,090, which you have to understand the principles of decimal number formation to make the name. So if you analyze the names, the arithmetical operations by which we make numbers from the base 10, such as multiplying powers of 10 by coefficients up to 9, then adding them up, all of them are now implemented grammatically because we have no writing. The real reason why people didn't pay any attention to the Rigvedic mathematical knowledge, arithmetical knowledge, is that there was no writing. No numbers were not written. They only had names. But names are as good a representation of numbers as written symbols are if you understand the principles. For example, that is how we read a polynomial. Nobody says 1, 2, 1. They always say x squared plus 2x plus 1. Okay, even though algebra texts still say that a polynomial is a sequence, an infinite sequence of which all but a finite number vanish. I was very amused when I read that. That's the way the Indians thought later. Anyhow, that's a different story. So So that keep this in mind, Rigveda is a linguistic resource for understanding numbers and the total mastery of decimal numbers that they had. The Vedic people had no writing. So that's one reason why this knowledge was not considered serious knowledge. Because, there was a tendency for historians to think that civilization began with writing. That is not true always, not only because oral history is a very, very powerful source of knowledge, also because in India there was no writing till about the beginning of the Common Era. Very little writing towards the end. But there was plenty of history, and we know that history. So, yeah. What is to be remembered from this slide is this last paragraph, in which I say that in nominal representation, that is giving numbers names, you don't need a zero. When you say 2022, there is no zero in it. You have 2020 and 2 added together. So there was no zero in Indian arithmetic as a place value symbol till approximately the time of Pingala. That's one of the points I'm going to make. However, zero as a number, not as a placeholder, but as an integer, as the integer before 1, the cardinality of the empty set. That is a notion Pingala brought to light for the first time. This is not part of the combinatorics, but it's subsidiary to the combinatorics. It arises in a very, very interesting algorithm. Oh, this map doesn't come through very well on the projector. Now, I've said all these things. All of this happened in the northwest of India. Northwest of India, this is the river Indus. The various tributaries. This is the main river. And this area pretty much covers the extent of the Indus Valley civilization. It was a very extensive civilization, very large areas, large population. And the people we are going to talk about in the beginning, that is Pingala himself. Before that, the great grammarian Panini. And after that, a couple of other people. They all worked and lived and worked here, this area, which is called Gandhara in the Indian tradition. Now, these people worked, Panini in 500 BCE, roughly speaking. Pingala maybe about 200 BCE. This was a time when very close contacts were established between India and nations and cultures to the west of India. For example, the great Persian emperor, Cyrus, founder of the Achaemenid line, he conquered this area, most of this area. And Panini lived probably under his rule. Pingala himself is about 300 to 50 BCE. And remember that Alexander of Macedonia came and occupied this area for a brief time in about 350, I think, 4th century BCE. So this was an area of India which was very open to outside influences. And this was also an area which was a crossroads of the ancient civilizations of the time. So when people say that, we are nationalistic people, we accept nothing from outside. We only give, we don't take. That's a grave distortion of history, very grave distortion of history. Every time the Indian civilization has done well, it's been open to other civilizations. And I think it is true of all civilizations. That's my view. I had to say this. Now, why is it not coming? Oh, there. Yeah? Someone said something. No, this is... Now, this is important. This slide is very important. It's not about mathematics at all, except in a very indirect sense. Panini was the greatest grammarian of the time, and according to many Paninian, according to many modern grammarians and linguists, he was the greatest grammarian of all time. Enormous amounts of material have been written on it. Very, very detailed, very technical, very difficult to read, very difficult to understand. The commentaries are often more difficult to follow than his own text. His text is very difficult. I once tried and failed. But when you go through all these things and you summarize in your own mind what it is that was revolutionary about his grammar, it is this fact that he thought categorically. He did not, there is, as I say, he classified all linguistic objects into sets, what we'll now call sets. The Sanskrit word is better translated as categorized. The category is not in the modern sense of the term, but categories in the original linguistic sense. And then he set down rules not for individual objects in a category or not for any individual object. All the rules were categorical. All the rules were stated for all objects belonging to a certain set. And the sets are formed based on the commonality of their function, or in some cases, on similarities in the phonetic sense. That is, for example, there are certain rules of language which depend only on the phonology. It doesn't depend on the semantics at all. So when that happens, you classify all things. For example, all nouns ending in the vowel A will be one class. All nouns beginning with A, E, will be another class. Then there will be a rule which says, how do you telescope them together? Instead of saying that, Nila and Utpala is Nila Utpala, what he will say is, the first category combined with the second category in that order, A plus E will become O, or A. So, so this is really, set theory without axioms. That's what it is. And all grammatical operations, all linguistic operations were reduced to maps from sets, including maps within each set, that is a map on itself. Then immediately it follows, you can combine such maps. Okay, if the initial set and the final set of one map agrees with the initial set of the following, the preceding map, you can combine them together. So he reduced grammar to set maps and their compositions. Literally, there were exceptions because, this is a natural language he's dealing with, old Sanskrit. So when the exceptions come, he tell you, these are exceptions, be careful. So, so you would think that Indian mathematics will take off from this point because, this is one of the using the structure of a set as defined by its, what you can do with it, is, for me, the most productive tool of modern mathematical thinking, including in physics these days. The Indian mathematicians had nothing to do with it. No, they didn't touch it. They never used categorization. Whereas our hero, Pingala, did. And for me, the true value of Pingala's work is not that he founded a systematic theory of combinatorics, but that he applied Paninian methods to a problem which was completely solvable. Okay, and Pingala's greatness lies in the fact that he did not, as earlier work, which sometimes are quoted as support for combinatorics, such as, for example, the Egyptian papyrus manuscripts. He was not dealing with individual puzzles. He was making a theory for a general theme. The theme is, how does one combine various objects which have different functions or which have different purposes? So it's a very, very categorical way of approaching a particular problem. The problem he was doing is, the book is called Chandas Sutra. It's a very difficult book to read because, since everything was oral, there was a tremendous demand on memory. And anything that was useful to enhance our memorizing power was taken over by the scientists, let me call them scientists, by the savant, by the people who made these subjects progress. And versification is a very effective tool of memory. It's a very powerful mnemonic device which lets you remember large quantities of things. Everybody remembers songs. They don't always remember prose passages. There were songs and things which have melody, things which have a structure, a rhythm. Those are easily remembered. So versification became very popular. So there was a problem. Can I have a theory of the means of versification we can have? That is the origin of Pingala's work. Now, what are meters? Now, before that, that I've already done that. Yeah, the historical context, I should say. At about the time that Pingala lived, writing came back to India. Writing was present in the Indus Valley civilization, but nobody could read it. It disappeared completely. It's totally different from any language which came to India later. It is ideographic. It is written from right to left. It dispensed with many linguistic devices, and it's unread. The writing which came in the middle of the 4th century BCE in India was very systematic. It's syllabic. The language is syllabic. The symbols represent syllables. It is not alphabetic. And Pingala, my feeling is that the reason why he decided to systematize the theory of versification is precisely because there was writing available and you could put everything down. I have no proof for it, but that's what I think. Now, during this period, many wonderful things happened. For example, mathematically speaking, they became extremely handy with negative numbers. Some negative numbers occur everywhere. In fact, they are metaphorically denoted as wealth as positive and debt as negative. And those are still the terms used in India for positive and negative. You say Rana Sankhya or a negative number, Dhana Sankhya or a positive number. All the texts use it. So that's already in the 3rd century text Arthashastra. So that is the other thing. Then numbers, very large numbers were, they realized very quickly that once you have the base 10, you can just go up in numbers without limit, no boundedness. You were not limited by a bound on the positive numbers. Result is that the word infinity doesn't occur in these texts, but there are any number of explorations of what it will be like if I then took the largest number I can think of and multiplied it by 10. What will happen? So many such speculations, and numbers were given names, and there are number names for things like 10 to the 55 in texts. And these are not mathematical texts. These are all texts which are basically, sometimes they are epic poetry. Ramayana and Mahabharata both have enormous numbers, of very large numbers. The Buddhist mythical writings also. So that is the background in which he lived. So what is a meter? Pingala made a theory of meters. And what's a meter? A meter is, first of all syllables in Sanskrit or most Indian languages can be said to belong to one of two disjoint subsets. One is called Laghu, L, La, and the other is called Guru, Ga. And Pingala himself named them, gave these sets names, and he indicated that one system, the short duration syllables are called L, the longer duration symbols are denoted by G for Guru. And I call them L and G, he called them La and Ga. I mean, he did it himself. I mean, it's not something which modern people have done. So a sequence, a line or a pada in a verse is a sequence of syllables, each of which belongs to one of the two subsets. So a meter is characterized by saying which sequence a certain line belongs to. That is to say, to every syllable, you attach the label L or G, depending on whether it's a short duration syllable or a long duration syllable. So these are now sequences, abstract sequences in two symbols called L and G. That's a line. That's the meter of a line. Now, a stanza can consist of 2, 3, 4, many lines. So when that happens, you have to say a sequence. First line is this meter. Second line is this sequence. Second line is this sequence. Third line is another sequence. And the whole thing is called a meter. But Pingala considers only one-line meters. That is to say, how to characterize meters which are defined by one line, one pada. And of course, he classified them all, and most of them were of complete lack of interest to any poet. I mean, a very large number of meters can be constructed, and most of them were not interested in any of them. However, yeah, my feeling is that that was just an excuse. What he really wanted to do was, what is the mathematics behind this? This has happened many times in India. Subsequently, mathematics was driven by astronomy in a big way. And a lot of people think that it is all astronomy, but there are lots of things also in the Indian mathematical writings in which astronomy is just an excuse, or sometimes not even an excuse. They simply say that, I'm an astronomer, but solve for me Pell's equation. This is what Brahmagupta did. These quadratic equation, Diophantine equation, it has absolutely no applications in astronomy. But Brahmagupta says it's very useful in astronomy, which is not. No, but the thing is, astronomy was a very glamorous subject at that time, because for several reasons, not always very honorable. Because one of the reasons was that the charlatans decided that if they can predict the trajectory of a planet by looking at initial conditions, you can plot the trajectory of a human being by looking at the initial condition. That is, place of birth, time of birth, and so on and so forth. So astrology, horological astrology became extremely popular. So everybody pretended to be an astronomer. So, it's I've done. Yeah. So in this work called Chandas Sutra, there are 5 propositions. I use the word proposition because that's the nearest I can find to the word he himself used. The word he used, they're called pratyaya. A pratyaya is a statement which either is obvious or has to be proved. So I thought, rather than say, or a construction to be followed, rather than get lost in terminological confusions, I will call them propositions because some of them are really propositions in the modern sense. Yeah, what are they? The first one is very straightforward. Find a canonical ordering that is given the sequence of L and G in a line, in a meter. Order them in some standard way. So there is no confusion, everybody follows the same order. And then second and third, given the ordering, if I tell you the index of a particular sequence in that ordering, what is the sequence of L and G? What is the meter that will come out of it? Okay. And the third is the opposite. That is, given the meter, what is its index in the list? The fourth is total number of meters of length n. The length is the number of syllables in a line, in a meter. So what is the total number of meters of a given, for a given length? And that's, of course, we all know the answers. All of them are very straightforward things. And fourth is, fourth I've done. Fifth is the one which this poster represents. That is, we'll say it's a statement about binomial coefficients, and the problem is, given a meter of length n, how many meters are there in which one of L or G is exactly k, when k is less than n? Okay. This is the one which everybody talks about, but actually, apart from the one, the others are quite interesting. Not because, none of them is very difficult. It's easy stuff. What is interesting is the way he answered these questions. That's fascinating. That's very modern. Yeah. The ordering. You can think of any number of ways of finding an order. What he himself did was, I have L and G, a meter of line length 1, first G, then L. Okay, that is the order for the length 1 meters. Then length 2, given any sequence, adjoin L and G, G and L in that order to the left of the sequence. Okay, so that's this canonical ordering. So this is unique. Once these rules are there, you cannot. There is a one-to-one correspondence between the index, which is in brackets, and the sequence, which is written out there. So to get all sequences of length n without duplication, all you have to do is adjoin G and L in that order to the sequence you already have in that order. So it's recursive. The way of doing it is assume that you already have solved the problem for n-1. To get from the solution to the problem for which n, just add first G on the left, then L on the left. So with this, on the left. See G, L, there on the left, G, G, then L, G, then G, L, then L, L. Oh, you can do many things. I mean, you can do many things, the one he says, take the first in the previous sequence, first add G to it on the left, then to the same thing add L on the left, then take the next one. Okay, you figure it out. Now there are many ways of doing it. I'll do some other way in a moment. It's okay. Can I go on? Yeah. So this indexing is basic because everything is fixed on this ordering. Sometimes, I tell you, all devices these days are quantum devices, same input, different output. Point at the laptop. Oh, I'm the quantum guy, not the machine. Yeah. Now, the thing is, this is an interesting question because, there have been lots of people, the natural question, did Pingala know about binary numbers? Because that's what they look like, sort of roughly speaking. My answer is no, because, time is it? Oh, I don't have much time. Yeah. Okay, don't worry. Yeah, my answer is no, because, if you take the sequence as he has described them, you try to read them, give the value L equal to 0, G equal to 1, or the other way, you will not get binary numbers in order. It's easy to see. See, for example, if you take this, this is 0, 0. If you want to start this way, this is 0, 0. This is what? This is 1, 0. It should be 0, 1 in order. So we have to read it backwards. There are many ways of doing it. The one I'm going to describe is very trivial, but it's very good. So you have to read it backwards, or you have to do something else. You can redefine G and L and read the sequence backwards, or read the sequence right, but read the list backwards, but every sequence in the right way. Or, there are 3 variables. That is the value you assign to GLR for two choices. The order in which you read the set of sequences, either right to left or left to right, or the order in which you read each sequence, left to right or right to left. Take any 2 of them to work out. So the thing is, But he didn't know these things, because if he was doing binary numbers, why would he choose a decimal index? He wouldn't. The second thing is that, to say, binary numbers, you have to know that there is a zero. And there was no symbolic zero in India for another 700, 800 years. It came much later. So, but the thing is, if you were doing combinatorics of a two-valued variable, sequences of two-valued variables, what else will you do? This is natural. This is completely natural. The thing is, binary numbers are, all knowledge is now a string of zeros and ones. So it's very popular stuff. Yeah, that's better. Yeah. Now, yeah. Now, this binary count variant is very useful because if you have it, for example, the list as is given there, the way to associate a given meter to a given index is take the ith entry in the list. I want to know the index I, what is the meter that it represents? Take the ith entry, look at I minus 1, because you want to start from 0. Look at I minus 1, write it down in binary form. Then you will get a certain set of zeros and ones, a line of zeros and ones. Add enough zeros on the left so that the length is n. You make sure that the length is n. Then you associate L and G with 0 and 1 in the correct form. You get it. So, for example, there are these examples. Pingala's way is not Pingala's way. That's the point. What he says is, if I is odd, then you know that the first one is G, it begins with G. So I is odd, then your meter will begin with G. Okay. If I is odd, put down G. You already know that. Okay. And replace I by I plus 1 divided by 2. So what it does is to give you the one which comes to the right of this, the first entry. And if can carry on. If I is even, then put down L. That's because the second one is L. And then carry on. Keep on, you keep on doing it. Iterate till you come to the end of come to all n of them. So that's what I illustrated here for n equal to 4 and I equal to 3. I equal to 3 means it's odd, so it's G. Then update I to I prime, which is 3 plus 1 divided by 2, which is 2. So you get L. Update it to I double prime, you get that, and so on and so forth. Okay. This is Pingala's way, by the way. It's not some modern historian who has done this. This is what he says you should do. No, 3 I have not described. It's just reverse the steps. It's so what's interesting here now is a method. The method, you've seen that now. It is everything that is done is recursive. It is as though repeating a step with minor changes, or repeating a step in which the next step will have as input the output of the previous step, is a standard way of thinking in all these things. And that's not only in mathematics, it's visible in rituals, and even today in Indian music, Indian dance, Indian theater, classical theater like Kathakali, for example. It's full of iterations of various kinds. The literature, Panchatantra, stories within stories within stories. So this is very strongly a mindset which, according to the great scholars of India's past, like Fpsac, who has been here several times, says that it actually has its origin in the rituals. Because in order to please the gods, you have to do certain things in a certain very precise way. And in order not to make mistakes, you repeated them so that one of them will be correct. And I think it's possibly true. I'm not very sure, but it's true. Now, the question arises, and not only is it recursive, almost all of them are descent methods. What you do is you take a problem and reduce the parameters which come in it in magnitude, bring it down till you reach the lowest possible level where it stops, or till you reach a level where you can solve the problem by inspection. So descent is Pingala's, the first use of descent consciously in Indian mathematics goes to Pingala. So, what have I done? Yeah, he was a great guy. So the question then is, you can also ascend, you can go up, which is also very popular. And that also was finally done in India, much later in 1400 AD, 1400 CE. Formal inductive proofs, which one can actually translate the text and one will see. He'll tell you, do this, do this, do this. And he says, the astonishing thing is, the guy who first wrote about the inductive proofs, he precedes it by an axiom. It's very rare to find axiomatic statements in Indian mathematics because everything should be obvious. Things which are not proved should be obvious. This is an axiom. The axiom is actually Peano's succession axiom. It says that the result of looking at the next number in this line of succession is the same as adding 1 to that number, to the predecessor number. That actually, when I first read it, it took my, I blew my top. I took my breath away. It's actually there in those terms, except then he says, he also introduces the notion of a predecessor. The predecessor of a number is what you get by removing 1 from the number that you have. So these are things which are not extremely well known, so it's not a bad thing to say these things. Yeah. Proposition 4 is about total number of meters of a given length, or length n. And of course, we know the answer is 2 power n. Pingala knew the answer too. Why? Because he knew that when you go from length n to length n plus 1, you have 2 options, add an L or add a G, uniquely, in a unique way. So every step multiplies the number of meters by 2. So if you take n steps, of course, you get 2 power n. But that's not what he does. What he says is, if what he says is, replace n by n of half n whole squared. That is, and this, if it's 2 power n, this is the correct thing to do. I mean, it's a true statement. But he didn't know it was 2 power n. He says his recipe is take n of n. You want to find n of n, okay? And you know, you replace it by n by 2, the number of meters of length n by 2 whole square if n is even, or remove 1, write twice, take 1, 2 out, you will be left with an even number. Take half of that, take the square, then iterate. Okay, so rather than explain all these things, two examples. N8, for example, according to him, is n4 squared. Descent again, n2 to the 4th power, n1 to the 8th power. One of length 1, there are 2 meters, so it's 2 power 8. If n of 7 is twice n of 3 squared, because I've taken 1, 2 out. Then I've taken 7 plus 2, 7 minus 1 divided by 2, which is 3 squared. 3 is odd, carry on. So you get 2 power, 1 plus 2 plus 4. It's easy to check. So why did he do this fancy factorization? Nobody has an answer to this question. I mean, many historians have written about this, and I don't know what the answer is. It's very, very curious fact. People say, modern people who know, who are literate in computer mathematics, they tell me that, oh, it's because the number of multiplicative steps is reduced, which is true, but the numbers get bigger. How do you get to the big numbers? By doing more multiplications earlier. So I don't know what the answer is, But this is what he does. I don't know the answer. Yeah, take 10 minutes. So as you can see, I have spent a lot of time on Pingala because, his thinking runs through all work on combinatorics in India later. Everything is recursive. Everything is, a lot of Indian mathematics is decent mathematics. It actually takes, for example, the solution of Diophantine equations. It's always done by reducing the coefficients. So it's quite remarkable fact. Yeah. So how did the zero come into this? In these intermediate steps, I said, if it is even, do this. If it is odd, do something else. So he says, call whenever you get an even number as the nth step, say that it belongs to a set. When you get an odd number, say that it belongs to another set. And these sets are given names. The names are 2 and 0, Dvi and Shunya. Shunya is the word used. And Shunya, meaning void, cannot but be 0, because Dvi has only one meaning in Sanskrit, which is 2. So this is the first inkling we have that the number 0 was understood. This is not in a place value context. It is a number 2, number 0, like 2 is a number. So, it's a remarkable man. He must have done that. Yeah. Or whenever you see a star on some words, what it means is that they are of Indo-European descent. And you can see Dvi is 2, which is the same in many European modern languages, and also in old languages. And I have also done this for things like pada, foot. They are the same word. Proto-Indo-European, they are the same word. This is very easy. This works very well. Binomial coefficients is my last proposition 5. Now here, there's been a fair amount of writing on the subject. And I have said somewhere earlier that the person who really made sense of what Pingala says by reading a verse which was not read by other people and by using the commentary of other people who came later is that this is done also by descent, but in a very unusual way. First of all, that there is a symmetry. K is the number of syllables, number of matras, number of syllables which are either L or G, doesn't matter. So there is a symmetry. The K is fixed. N is the length of the meter. The question is, how many meters are there in which of length N with K fixed? And we know the answer is the binomial coefficient Nk. But what he says is, to get all meters of length N with K fixed, without duplication, do exactly what you have done before. Adjoin L to every meter which has K minus 1 Ls. So the number of Ls now gets updated to K. And adjoin G to every meter of length N minus 1, but K unchanged, because this G doesn't change the number of Ls, just increases the length. Okay. So what does that do? It gives you a recursion relation. Gives you the recursion relation which says Nk is N of N minus 1 length and K minus 1 Ls plus N of length N minus 1 and K Ls. So this is the recursion relation. You want to solve this. That's Pingala's problem. And what he does is, of course, not surprisingly, descent. Well, we know now that this is exactly the binomial coefficient recursion relation. So we won't do any work. We'll say, oh, I have got the binomial coefficients. But Pingala's solution is, take the second term, this term. You see here, we have reduced K by 1. Here K is the same, Now apply the same recursion relation to this term, which means n minus 1k will replace n and k, and this will become n minus 2 k minus 1, and then there will be an extra term which is n minus 2k. That's what you'll get. Repeat. This is what you'll get. At a certain point, it will terminate because k must be equal to n maximum. It cannot be more than n, because there cannot be more else than the total length. The result is that it terminates. So you have a iterated recursion relation. Now apply the same recursion to each of these terms. Okay, so you'll reduce the k a little by n, and you will reduce k little by little till n minus the n and k. N will become less than the k in each of them. Okay, stop there, add them. Okay. He doesn't give you the answer, he tells you what to do. And presumably what he does, according to Jan Shah's name I mentioned in one of the slides, that's very good reading, by the way. He's terrific, excellent piece of work. So when you do that, what you find is that you can plot this as you can plot the n's as points in the nk plane. You start with n equal to 2, k equal to 1, which is equal to 2, by the way. And then you plot it, and what you get is what this picture tries to say. This is the Suji Prastara. Okay, you get actually a variant of the Pascal triangle. And this was done not by Pingala. The graphical representation is not due to Pingala, it is due to another combinatorial guy, performance arts combinatorial guy, I should say, named Halayudha, who lived much later, who lived in the 13th century. So, of course, Pascal did it too, somewhat later. Now I'm going to skip this very large, not very large, a fair number of very, very brilliant people who contributed to combinatorial mathematics in India in a very systematic and productive way. I just mentioned the names. Bharata, who is the person who wrote the Natya Shastra, who's a text which is still in use in India in the performing arts, in dance and drama and music. Virahanka is a very remarkable guy. I'll come to that in a minute, so I will skip that. Halayudha, I just mentioned, he's the one who plotted the first Pascal triangle. Sharangadeva wrote a book called Sangeeta Ratna. Yeah, now I'm back to normal. Sangeeta Ratnakara, Ocean of Music, which is an extraordinarily rich book and extremely complicated combinatorics, because we're dealing with music, and music has 7 notes and 4 tempi, 4 matras. And so you have to, you get fairly complicated, hairy stuff. And it's all worked out. And the real breakthrough due to Sharangadeva is that he not only did the Pingala stuff, that's the kind of things that straightforward combinatorial stuff that I already described, but in this larger context, he also did things like finding generating functions for these coefficients. You get all kinds of wonderful numbers, sequences of numbers. For each of them, find a generating function, so like the binomial series. The binomial series, the coefficients come by expanding 1 plus x power n. So that's the kind of thing that was done. And for this, there is an absolutely magnificent review by our good friends, Raja Sridharan, R. Sridharan, and MD Srinivas. Very, very good. And it's very easy to get because it's in the CMI History of Mathematics seminar volume, edited by Sheshadri. And finally, I will mention Narayana Pandita, because he was another of the people who have been ignored by historians for a long time. Even though his name is known, nobody has given him credit. He did everything. He did geometry, he did algebra, he did number theory, he did magic squares, he did combinatorics, and all of them at a very high level, one of the greats, one of the greats of Indian mathematics. So I do some technology is not easy to master, I have to say. Very quick. One of the things that Virahanka did was, in music, very critical is the length of a cycle in time, the duration of a cycle in time, because there is the rhythm guy, the guy who beats the drums, and he has to have a pattern to follow, and which is strictly cyclic. And the singer has to fit his performance into that. And the singers, both of them can combine various tempi, long, short. I mean, like, for example, in the traditional Indian way, there are 4 tempi. There is Dhruta, Laghu, Guru, and Pluta. 1, 2, 4, 6. And all Indian talas are based on this counting, with some exceptions. And so they have to match. So duration. So question is, the first part of, the thing is, a guru lasts twice as long as a laghu lasts. So the question is, what is the time duration? For a given time duration, how many talas are there? How many rhythms are there? And the problem is not very, it's actually simpler than some of the earlier Pingala things, because what you do exactly the same thing. To get to duration n from n-1, you can add a g to n-2 because it is twice as long. Or you can add an L to n-1. So you get this recursion. I mean, that is the Fibonacci numbers. So this is, and here again, I have given a reference to Parmanand Singh, the wonderful little article, not very little, very nice article on the complexities that you can build on this basis. And Parmanand Singh is, I think, no longer alive. He's a very distinguished man. He's done very fine work. Not very well known, unfortunately. Those who want to read more, I can. You don't have to note down anything. I can give you the references later. A change of scene now. I want to now give a hint of how very, very beautiful advanced mathematics that a man called Madhava did in the 14th century, the end of the 14th century. And what he did was actually to invent calculus. That sounds like a very irrational claim, but it is strictly true, speaking true. How many people here have heard the name of Madhava? Oh, that's much better. If I'd asked this question 10 years ago, not a single hand would have risen. Yeah, he was one of the titans of mathematics, not only Indian mathematics. He actually did calculus for trigonometric functions in a way which is much sounder than Newton's. It's very similar to Leibniz's approach to calculus, not Newton's. Newton is very, Newton is a very focused person. He knows where he wants to get. He'll get there by hook or by crook. So, for example, he himself will say, I shall do this by analogy. Actually, he has actually written this. So, extrapolation and analogy. Now, Madhava's work is on calculus. One of the things he is well known for now is the development of the sine series, the power series for the sine function. He did it. What he actually did, I'll come to in a minute. But the method is very simple. You want to compute something which is a non-linear function of the variable. You linearize it locally. You cut it up into divided by n. For example, rectification problem, take the length of the arc, divide it by n, and do all your calculations as though the arc is a straight line at each point locally, and then add them up and take the limit and go into infinity. Okay. No philosophical confusions about what is meant by an infinitesimal, no such things. So So Madhava did this for several things, you know, it's really beautiful stuff. And then, for example, recursion, the power of recursion. How did he solve, how did he find the power series for the sine? In modern language today, with infinitesimal calculus familiar to all of us, this is what he did. He set up the differential equation satisfied by sine, turned this into an integral equation. And this is the integral equation. This. What you do now is you have sine z here, substitute for sine z this expression, the whole expression, because that is what sine x is. So you get a series of terms with multiple integrals. And the first term will be, in the first term, what will there be? This x will be, you know, in the first term in this will be another x. So you'll get x squared integrated, you get x cubed divided by x squared. X squared divided by 2 integrated again, you get x cubed divided by factorial 3. So that's what he did. It's very elegant. Now, how many of us have done the sine series in that way? Very few, I'm sure. Then, what he actually did was doing all this not by taking the limit, but before taking the limit. Then you get this hairy equation. This equation. This is an equation for sine x in powers of sine x divided by n, or x divided by 2n. Depending, you can choose any n you want. This is a generalization of the formula. Sine theta is 2 sine theta cosine theta for general division. And it's very difficult, it's very hairy stuff to get there. The coefficients are not explicitly given. Coefficients are shown to satisfy this recursion relation. You see, the coefficients are, they increase. This index increases, the n decreases, and coefficients are defined by sk of n is the previous such sum.
I'm sorry, Professor.
Previous such sum, but indexed by I and summed over I from all the way.
I'm sorry, could you please finish in 5 minutes, something like this?
I will finish in 3 minutes.
3 minutes, okay, perfect.
Finish in 3 minutes. Now, this is very beautiful stuff, you know. So you do that, and when you do that, you get these things satisfy the recursion relation, Skn, Sk minus. This is what you get. You separate one term and you do all these things, and finally what you find is that this equation has a solution which is also a binomial coefficient, and it satisfies the recursion relation is the same as Pingala's recursion relation. So it comes in all kinds of unexpected places. Yeah, this I don't have to say. This is just. This is vague generalities. Yeah, that's it. 3 minutes, I said 3 minutes.
Thank you for your.
I thought I had it. I thought I had my talk under control. 1 hour. No, it took a little longer. Yeah.
Are there any questions or comments for the talk?
Oh, you have. I know now. Dinner is weighing on everybody's mind. Yeah, you know. Yeah.
You have spoken about the pioneers of
Yeah.
combinatorics in India.
Yeah.
Could you say a little bit about dissemination? How did they disseminate the work? How widely was the work? You know?
Very difficult question to answer, you know, because as I said, all these people worked in an area in which there was a tremendous amount of traffic. You know, there were many Greeks because this was part of Alexander's Indian Empire. Seleucus was the governor, and there were very close contacts during the 2nd, 3rd century BC between Northwest India and Alexandria, for example. Okay, but we have no evidence. We have really no evidence. In fact, I have often felt that the only evidence we can look for is mathematical commonalities, because historically there is no evidence. Yeah. What about things which flow into India? In the other fields, we know that there's plenty of borrowings. Like, for example, architecture. Many features of Indian temple architecture, Buddhist architecture, are borrowed from classical Greece. That's well known. Also in sculpture, certainly it's in that style was even called Indo-Greek at one time, because it is this influence of the Athenian and the Alexandrian sculptural tradition is very strongly visible in Gandharan sculpture.
I'm sorry, actually I was referring to the work that Pingala did within the community that he lived in. Do we have any idea about, was he working in isolation, whether
No.
schools or whether...
No, we have no
disciples?
no knowledge of him as a person at all, none, nor about the society in which he lived. Okay, we really don't know. We don't even know exactly where he lived. There is about, for Panini, we have some information. All we know is that he was from that area. And that was a hotspot of cultural exchanges at that time. That we don't know. We cannot be more specific. Yeah. And there's a lot of work to be done, Yeah.
I have quite a few questions, actually.
Oh.
So, yeah, I know. So firstly, when Pingala was calculating 2 power n, he gave this algorithm in terms of going to n by 2 or n minus 1 by 2.
Yeah.
Did
Yeah.
he justify that? Because I mean, to us, 2 power n is
No,
obvious.
he justified nothing at all.
I see.
His sutra style, it cannot be read by ordinary people. It can only be read by people who have deeply absorbed his way of thinking over many generations. So it is not for nothing that the commentators are always a few hundred years later. It takes time. And reading, Panini, for example, I have friends, very, very fine scholars of grammar, who say that we understand Panini much better than, let us say, Bhartrhari did, who was a great grammarian himself, who lived in the 5th century. Time, these are very compressed aphorisms, and it's very, very difficult to pierce into their ways of thinking. So that's one reason I think, you haven't given me another minute. I give an example of something which I know from my own experience, my own work. There are passages in Aryabhata's great work on mathematics and astronomy, in which he uses the word Brahma. Okay, for a very long time, people thought that it referred to the god Brahma, which in Sanskrit is a masculine gender word. In our work, we came to the conclusion that it doesn't make any sense for it to be Brahma. So, but if you look at the declensions of the words which follow, or Brahma itself, you realize that this Brahma in Aryabhata is not masculine, but neuter gender. So it referred not to the God, the creator, it referred to the Brahman, Shankaracharya is Brahman, the pervading spirit that runs the universe, which is not a personalized God. This, it had to wait till 2020. It makes no sense, no, but this happens. It happens all the time.
Okay, my next question is, so Pingala defined the even and odd numbers, and he referred to them as Dvi and Shunya.
Yeah.
Wouldn't it have made more sense to refer to the odd numbers with, say, Eka, which is 1? 1 is actually odd.
I don't know. Yeah, that occurred to me too. Why didn't he say 0 and 1, for example, or 2 and 1? Yeah, I don't know. I don't know the answer.
So, is this the first time the word shunya appears in any text?
This is the first time the word shunya appears in the sense of being 0. Yeah, shunya as emptiness or void was known before. But in grammar, there is a situation in which there are certain things which disappear, which are not there, leave an empty space behind. Shunya is not used for that normally. Normally, the word used is lopa. lacking in something. Yeah, but as a number, this is the first time. As far as I know, huh? Subject to correction. Who? No, Panini doesn't use the word shunya, he uses lopa. Yeah. And that's well understood. He's from Kerala, so you will know something of the Sanskrit grammar. There is a samas called madhyama pada lopa, which is there is a middle word. When you bring them together, you drop it without changing the meaning. And it happens all the time. It's in Sanskrit grammar. So lopa is used in that, many examples are given. It's not replaced by a symbol which says 0, by the way. Oh, still. Wow, I should have taken less time.
So, just a comment on this. So he's really, the shunya comes as 2 raised to the power 0 equal to 1. And then dvi is 2 raised to the power 2. Because he's describing 2 raised per something, right?
Anything raised to the power 0 is 1, so why 2?
No, so he's in your algorithm, he's calculating 2 raised to the power n, and
Yeah.
he's reducing it down. So these are the last 2. So it makes sense to say shunya is 2 raised per 0. Huh? No, 2 raised per 0 and 2 raised per 1. So so I'm just
But
saying,
the exponentiation, 2 power n, you will not find in Pingala or anywhere else. The Indian arithmetic people had 4 major operations, the usual ones, plus 2 other operations, square and square root, which were considered fundamental operations. But exponentiation was not considered a fundamental operation, because if you did, you would not need new names for powers of 10. You would simply say 10 power 2 for 100. That is not the case. You say shata. You don't say dvidasha, for example. You don't say that. So exponential functions were not considered seriously in India. Yeah.
I think that Professor Divakaran is invited to the banquet. Yes. And so,
What? Sorry again. What?
So you have a very popular talk, and you have plenty.
Thank you very much. I'm a very tired man, so we'll see. Thank you. Thanks, all of you.
yeah, so I remind you that we meet at 6:30 behind this building near the staircase, near the parking lot. There'll be 2 buses there. Yeah, exactly. We will meet exactly where we met for the excursion yesterday. So we have 10 minutes